Good afternoon and good evening, everybody, and welcome to the FDL 2020 Space Science and AI Showcase. Be prepared to have your seatbelts buckled because we're going to be taking off soon. And I think you're going to hear some extraordinary work from this year's researchers who are once again pushing the boundaries of AI as applied to space science and technology. We've got a great program lined up for you today. So I want to welcome you all and also welcome our guests, our participants, researchers, our mentors, our partners to the windup of this extraordinary year and this extraordinary FDL program now in its 5th year. So without further ado, let me turn this over to my colleague, Sarah Jennings, and also James Parr, the director of the FDL program, to describe the program a little bit and get us started here. So Sarah and James.
Great. Thanks, Bill. Really excited to have everyone here today. Frontier Development Lab is an applied artificial intelligence research accelerator. We bring together the brightest minds from around the world in space science domains, and we pair them with machine learning researchers. Our researchers come from backgrounds in industry and academia at the PhD and postdoc level. They go through an intensive 8-week program where we provide them with massive amounts of compute, unique data sets, access to leading experts, and a critical support system of our faculty to help them tackle their challenges. So as Bill said, FDL is now in its 5th year, and it's hosted by the SETI Institute in partnership with NASA. So with that, I'll turn it over to James, or Bill.
All right. So I'm going to just tell a little background story of the program to give a little context for what this is all about and where we are now. So 5 years ago, in the summer of 2015, I received a call from the Office of the Chief Technologist at NASA headquarters. I was only 2 months in as the new CEO of the SETI Institute at that time, but needless to say, that phone call got my immediate attention. NASA had 3 questions and 1 proposed proposition that they put forward at that time. And the questions were as follows. Number 1, could AI and machine learning tools and techniques be applied to basic research and NASA science to help advance understanding, accelerate new discovery, improve process, lower costs, and mitigate risk? Number 2, could interdisciplinary teams of graduate AI ML researchers and domain experts in the natural sciences work together in an intensive summer research accelerator and achieve meaningful and impactful results? And number 3, could NASA engage private industry in a public-private partnership to bring hardware, software, compute resources, funding, and subject matter experts to bear on supporting such a research endeavor? A UK company called Trillium Technologies had been engaged by NASA to help architect these ideas into a program, and the proposition was to have the SETI Institute bring the program to life. This request was based on our long history of supporting NASA science, as well as our location right here in Silicon Valley, which is arguably the epicenter of artificial intelligence in terms of both the enabling compute technologies and resources and the development of cutting-edge AI ML algorithms. Oh, and there was a 4th question: could we start next summer? So it took me less than 3 nanoseconds, yes, I timed it, to say, yes, let's do this. So we met together at the Institute in October with folks from NASA headquarters, NASA Ames Research Center, and James from Trillium. We agreed that the answer to all 4 questions was a resounding yes, and in the summer of 2016, the very first FDL program was launched with 3 teams gathered at the SETI Institute focusing on 3 different topics under the domain of planetary defense. Fast forward 5 years and we find ourselves at the end of another extraordinary summer of new and groundbreaking research, with 8 teams having worked across 4 distinct domains against the constraining backdrop of a global pandemic. FDL by the numbers, which you can see on the slide here, is an impressive collection of statistics, with the first 4 years captured in this image, although James has now updated it to capture some of the image from some of the statistics from this year. The program boasts over 140 researchers from more than a dozen different countries, with women comprising nearly 40%, and minority groups making up 20%. We've launched 34 unique machine learning workflows. The program is also highly selective, with more than 1,000 individuals applying to participate. FDL research has touched on planetary defense, heliophysics, space resources, astrobiology, exoplanets, astronaut health and space medicine, and earth science. And it's been supported by more than 60 mentors and over 100 guest experts. FDL researchers have presented at scientific and AI ML conferences across the globe, including 12 presentations at NeurIPS, the world-renowned AI ML conference, and 6 at the AGU conference. And we've enjoyed the partnership of more than 10 of the world's leading companies in AI, ML, chip technology, and aerospace. There are 4 different space agencies participating in the program. And new partnerships this year include the US Geological Survey, MIT, and the world-renowned Mayo Clinic. It's been an honor and a privilege for the SETI Institute to host and administer the FDL program in partnership with NASA Ames and our corporate, academic, and research partners. And I'm looking forward to today's team presentations with great anticipation. In closing, before I flip it back over to James to take us into today's activity, it's worth highlighting the extraordinary additional challenge that was confronted by this year's teams, who managed to carry out their work without ever once having the opportunity to meet together in person. The COVID-19 pandemic resulted in this year's program featuring not only cutting-edge scientific research, but also a social experiment in testing our ability to collaborate and do extraordinary team-based research in an entirely virtual environment. I have to say my hat's off to our amazing researchers, our mentors, and our staff who managed to overcome the odds and once again push the boundaries of AI and space science. And with that, let me have James take us a little deeper into the FDL program. James?
Thanks, Bill. Sometimes we think of FDL as being a little bit like a rocket itself. We basically take geniuses from both the planetary and space sciences and put them in a room with machine learning PhDs and postdocs, also geniuses, and combust them. And out the back we get this great acceleration, and we have the exhaust of science papers and peer-reviewed papers. And of course, we love that. We love our work getting into journals. But we're also learning how to deploy our solutions, and this is again, getting machine learning solutions deployed is a thing where everybody's learning how to do, and we're figuring that out as well. Because of course, systems which are deployed need to be trusted, and you can't have trusted AI without really understanding explainability. And this is something that certainly at FDL we invest a lot of time in. And I wanted to thank our faculty for really being champions of this, because of course, we want to take a leadership position in machine learning for these sorts of applications. But this chart really shows, if you like, the exhaust of what we've done needs to be updated for this year, and I'm looking forward to adding to it. But we're also in the business of data products. So our teams make a huge amount of really useful contributions in the form of enhanced data sets. We've had one startup, and there are sort of rumblings of others. But also what we found is that our solutions are starting to cluster. So we're building these clusters of expertise. So this is, again, we're really excited to add to this chart, and I'm looking forward to seeing what the teams have come up with. This diagram is just a reminder that our, if you like, special sauce is interdisciplinarity, which and the best time to pull teams together is in the summer. But actually, FDL is a year-long activity. It starts with challenge definition all the way through to recruitment, and then we produce papers in the fall, and we use the NeurIPS, the Neural Information Processing Systems workshop, as if you like the bookend to our calendar. But I really wanted to call out all of the amazing folks that are involved all through this calendar year. And we often don't talk about all of the brainpower that happens either side of the sprint. And this is, of course, all of the people that contributed ideas this year. And there are lots of fantastic contributions. And I really wanted to just take a moment to say thank you for everybody who's been involved.
Thanks, James. And so now let's talk a little bit about what's happening this year. So this year, we've had 8 teams that have been given challenges in the areas of astronaut health, lunar exploration, earth science, and heliophysics. This year looked very different than our past realities. So on the picture on the left, this is a team photo of us spontaneously at NVIDIA. And this is more of what our team photo looks this year. We've been tackling things like time zones, connectivity, and new tools, and our teams embraced this new world, and they engaged with each other in exciting new ways, connecting and bonding. And they also did some really great work, which you guys are going to see today. So with that, I'll turn it back over to James.
Yeah, I think the other thing which really goes without saying, and Bill mentioned this, is we couldn't do this without our partners in Silicon Valley. And just as a sort of data point, which is perhaps interesting, when we started 5 years ago, our models were pretty small. 5 years later, our models are approximately 700 times bigger. And this is this observation that the pace of AI is far faster than Moore's law, which is this idea that computing doubles in speed and halves in cost every 18 months. In AI, it's every 3.5 months. And one partner in particular, Google, really has been fantastic in helping us, if you like, sort of get up to speed with the cutting edge of what's possible. And I wanted to just quickly say hi to them, and I know they'll be watching, and say thanks so much for another great year. And I know we have Scott joining us as well, but also our other partners as well, who've been along for the ride with us, Intel, IBM, and NVIDIA. Really, we couldn't do it without you guys, and I wanted to say thank you.
All right, so we're back to where it all started this year, and what you see before you is a screen capture from the Zoom meeting that we had as we kicked off the program back in June this year. And we have an event with every FDL program every year that we call Boot Camp. The Boot Camp is essentially a 1-week, highly intensive deep dive into AI and machine learning, where all the participants, including those who come from the AI and ML arena, kind of get brought up to speed on the latest developments mostly from our technology partners, corporate partners, and also NASA partners, and learn about the tools and techniques and hardware and resources they're going to have access to for the summer sprint. Normally, we do this in the very first week of the program, and then the researchers have 7 weeks to do their work, actually 6, because in the last week they're preparing for their presentations like you're going to see today. This year, we actually took the boot camp and moved it before the program started, just to give the researchers a little more time to adapt to this virtual environment constraint. So here's a picture of some of the folks that were on that first call, and you see here on the right-hand side, Dr. Eugene Tu, the director of NASA Ames Research Center, and I'm going to introduce him in just a moment for some opening remarks. But I do want to say as well, just to echo what James mentioned earlier, we couldn't do this without our partners. And I do have to give a special nod to Google Cloud because of the amazing compute resources they've put at the disposal of the teams. James mentioned the fact that the compute cycle requirements were 700 times more this year than they were 5 years ago. And that's extraordinary. And one of the things about having access to this incredible compute is the ability of the teams to iterate very quickly, to take and crunch data. And instead of having to wait days, weeks, or in some cases even months for the results that would happen with conventional compute technology, they're able to wait, days, hours, or even minutes to be able to see what happened, what results were achieved, and iterate again. So Google has been just a remarkable and extraordinary partner, transformative to the program. And of course, we've also benefited from Intel and Lockheed Martin and IBM and NVIDIA and all our other partners, including our new partners this year that bring some extraordinary new resources to bear. So thanks to all of you for all your partnership. And let me now move to introduce Eugene to you all. So those of you familiar with the FDL program have heard about Eugene before, and you've met him because he's been kind enough to speak at most of our public events over the past several years. But Dr. Eugene Tu is the Center Director at NASA Ames Research Center, where he leads staff of civil servants and contractors in providing critical research and development support that makes NASA's and the nation's aeronautics and space missions possible. Eugene was most recently Director of Exploration Technology at Ames, a position he held from November 2005 until his selection as Ames Center Director in May 2015. In fact, both Eugene and I took on our leadership roles at about the same time, and I remember our first meeting together around late May in 2015 over at Ames. So there he has led 4 technology research and development divisions, including 2 of NASA's critical infrastructure assets, the Consolidated ArcJet Testing Complex and the agency's primary supercomputing facility. Dr. Tu earned his bachelor's degree in mechanical engineering from the University of California, Berkeley in 1988 and both his master's and a degree and doctorate in aeronautics and astronautics from Stanford in 1990 and 1996, respectively. He's an associate fellow of the American Institute of Aeronautics and Astronautics, AIAA. He received the NASA Outstanding Leadership Medal in 2000 and the Presidential Rank Award for Meritorious Executive in 2009. Eugene lives here in the North Bay with his wife and 3 children, and his hobbies include attending sporting events, playing music, traveling, and motorsports. And I recall one of the first virtual meetings that Eugene and I had together where we were both at home, and I looked at the pictures in his office behind him, and they weren't of rockets, they were of like fast cars. And I said, Eugene, where are the rockets? And he said, Bill, it's all about fast cars. So with that, let me turn the podium over to Eugene to welcome all of you. Eugene, take it away.
All right, thank you, Bill. Welcome, everyone. It is a great pleasure and honor to welcome and help kick off this event. And building upon, Bill, what you had mentioned at the very beginning in your intro, it almost mirrored my experience with FDL as well. I had just become center director at Ames, even though I'd been with NASA for my almost entire 36-year career. I just become center director here at Ames, and I got a call from headquarters, from the chief technologist office saying, hey, we know you're new and we know you've just taken over the center, but we've been working this opportunity with SETI, and we think this is something we ought to pursue. And so just like Bill, I probably took 2 nanoseconds, not 3, but we can debate that. But it fit right in with what our center does as one of the research centers for the agency. And of course, one of our primary areas of focus in AI and machine learning for the agency. And so it's been incredible. I've seen this program grow. When you take over a center, especially one like Ames that has an 80-year history, you often don't get to see things start on the ground level, and you're often coming in when there are programs that are in place and moving forward. But this really was a great opportunity for me to with Bill and the other partners to get in on the ground level and start something new that would really take the technology and the field and the applications to a new level. So it's been an incredible partnership. I think it has actually grown every year in the last 5 years. And as Bill and James mentioned, this year has been particularly challenging because of the pandemic. And the need to handle or do this virtually. It's been challenging and maybe in some adversity there, but I think we would all agree often the best results and the best answers and the best solutions come out of a adverse and challenging environment. And I think that is definitely the case here from what I've seen. It's been a great public-private partnership as well, especially as you look. I can't thank enough all the folks who have participated and supported and been partners and sponsors and funders of this activity over the years, and this year in particular. It's been a great public-private partnership. And if you think about some of the things that have been accomplished just in the short time that this program has been going on for this year, in the last few weeks, we have completed one of the biggest public-private partnership activities for NASA, and that is the successful launch and return of astronauts on a commercial crew vehicle, and that's the DM2 mission, which will actually completely change the way we do human spaceflight in the future. And then, of course, sending off Mars Perseverance and Ingenuity to Mars for an outstanding and incredible mission that is actually, for many of you might not know, the first of a series of missions that will ultimately result in Mars sample return, which will be the first round-trip mission ever to another planet, and ultimately something that leads to human exploration and settlement of another world. So if you think about all the things that AI and machine learning are going to enable and are absolutely required, these are just examples, and I think it's incredible, and I'm very much looking forward to seeing what the teams here have come up with. And then I'll just close with saying that I offered this at the boot camp, and I just want to reiterate it. Since all of you have had to be virtual, since all of you would have had an experience here with SETI and with the partner institutions locally and with NASA Ames, I certainly welcome and invite if any of you are in this area or find yourself in this area or partnering with us in the future, you have an open invitation to come visit, and we'd love to give you some of that experience that you weren't able to get this session. But I know the outcome and the products are no less incredible based on what you've been able to accomplish. So again, welcome and thank you, Bill. And I think I'm turning it back over to Sarah.
Great,
Actually,
thank you.
I'll jump in here just real quick, Eugene, but thank you very much for those comments. And I echo your invitation to all our participants and mentors and friends. Hopefully, before 2025, they'll actually be able to come and see us in person. And I just wanted to say, Eugene, that first of all, I yield you that nanosecond. So you're a little faster than me. So understood. But every year we've been, as you said, the program has expanded and grown, and it seems to get more amazing every year. This year being no exception, I'm sure I'm prepared to have my socks blown off, as has happened in previous years. But unlike previous years, this year I am prepared. I brought extra socks along for the ride. So with that, Sarah, let me turn it over to you and let's get us underway.
Great. Thank you so much, Bill. And thank you for Eugene. And thank you for the invitation to come back and visit. So with that, we're going to go ahead and start diving in here. So I'd like to introduce our esteemed panelists that are joining us today. So our first panelist is Aaron Pina from NASA headquarters. Aaron, would you like to say hi? Oh, I think you're muted.
Hello, my name is Aaron Pina. I am a deputy program scientist at NASA headquarters in Washington, D.C., and I'm in the Earth Sciences division. Just wanted to say hello, everyone, and thank you all for a wonderful summer. I'm excited to see all of the projects today.
Great. Welcome, Aaron. And next we have Scott Penberthy, who is the Director of Applied AI at Google Cloud. Scott.
Hey, everybody. And if you hear some piano music while I'm talking, I've got a neighbor who's a pianist for the San Francisco Orchestra. So you may hear him practicing next door to me. So a little bit of, just what we're all dealing with is we're working virtually. I think the teams have done fantastic work. And, so I'm really looking forward to, little color commentary as we go through this today. And as NASA likes to talk about rockets, and we hand them a rocket from Google Cloud. And what they've done with it is extraordinary. So it's going to be fun to see what the rides that they took.
Great. Thank you, Scott. And thank you for bringing some extra ambiance. And our last panelist is we have Rodney Martin, who is a part of the Intelligence System Division at NASA Ames. So Rodney.
Good morning, all. Thanks again. So I guess in some sense, I'm representing the data science community here. At Ames Research Center, where I'm a deputy group lead for the data sciences group within the Intelligence Systems Division. And also, I'm bringing sort of perspective of transformation and data from the agency level as I'm on detail currently within the CIO shop. So really excited about all of the great work that's been going on this summer and to participate as a panelist here for all of the teams.
Great. Thank you, Rodney. And thank you to our panel. So we'll hear from them after our presentations from the teams. But we also want you as an audience to help us this year with some of our awards. So we have asked our faculty to nominate our collaborative spirit, which is, as it states, somebody that within FDL has embodied being collaborative across teams and within their own group. We also have the heroic comeback, which they've provided us a person or a team who has been able to make a comeback throughout FDL. And then here's where we'd like your help. We have a couple of awards that we're going to have you guys vote on. So there are two ways to vote. You can either use this little a QR code, or you can use the bit.ly. It's also on the live stream, and I believe we're going to be posting that on social media channels as well, so you can vote. Unexpected discovery is really for a team that has been able to, throughout their research, find something that was unexpected. We also have the most dramatic pivot. So this is a team that might have started out working on one particular challenge and approaching it in a particular way, and through some happenstance made a big pivot and changed to something completely different. So keep an eye out for that. And then most useful contribution. So this is really a contribution that is worthwhile and is beneficial to humanity. So we're going to be asking that you pay attention to the presentations and take a moment to vote when we'll announce the winners at the end. So with that, I'm going to kick it off with our Moon for Good team. And to introduce them, I'm going to have one of our partners from the Luxembourg Space Agency, Bob, be able to present that team. So if we can play Bob's video.
Hello from Luxembourg. I'm Bob Lomboré and I'm working at Luxembourg Space Agency. We have been supporting FDL now for many years, and we are doing this in the frame of the Space Resource.lu initiative, in which Luxembourg aims to contribute to the peaceful exploration and sustainable utilization of space resources for the benefit of humankind. Last year, the Moon for Good team used unsupervised machine learning to understand and extract valuable information from thermal measurements of the lunar surface and was able to produce some amazing results. Following that very successful challenge, we are very happy that this year again, together with FDL and their partners, we came up with another inspiring challenge on space resources. This year, the challenge consists in producing high-resolution maps of the permanently shadowed regions. We believe that these maps will be an important information to find the ice on the lunar poles and will contribute to a better planning of the future lunar surface missions. The polar ice is a very important space resource, as it might change space exploration forever. Once we know where it is and we learn how to use it, we can, for example, produce propellant for rockets or water and oxygen for astronauts. We are very excited to see those maps. Now, I'd like to introduce you the team.
Thanks, Sarah and Bob, for the introduction, and welcome everyone, and thank you for joining our presentation. My name is Ignacio, and on behalf of the Moon for Good team, we're very excited to introduce the results of our work this summer, in which we focused on applying machine learning to improve lunar maps that could help with the identification, localization, and prospection of water ice. Before I kick off this presentation, I want to quickly acknowledge our advisory team, Miguel, Dennis, and Alison, as well as our partners, Luxembourg Space Agency, Google Cloud, Intel, and NVIDIA. We're very thankful for your support. 2020 has been a challenging year, no doubt. On the bright side, as Eugene mentioned earlier, it's been a productive year for the space sector with very important missions and a lot of progress made. And this year also kicks off what will be a new era of space exploration with even more ambitious goals for humanity. So what's next? We're going to the moon, and this time for good. NASA's leading a new era of space exploration with plans to return astronauts back to the moon by 2024 through the Artemis program. However, NASA won't be alone in this endeavor. Together with international partners and the private sector, we will start the development of a permanent lunar outpost. This will pave the way for long-term scientific and economic activity on the moon, as well as for the first human missions to Mars. But in order to realize this ambitious goal, we're going to need to take advantage of the resources that we can find on the moon. Among those, the most important one is water. Water can give us new insights about the story of the moon and our solar system. From a practical standpoint, water can be used as life support for future astronauts. And most importantly, it can be broken down through electrolysis into hydrogen and oxygen to meet a variety of needs, including rocket fuel, which could enable interplanetary travel. So water gives us a new paradigm for future space exploration. With the planned impact of the Alcross spacecraft in 2009, we were able to measure and for the first time confirm that water exists at the bottom of the Cabeos crater near the South Pole. Several other studies have also found evidence that suggests that water is abundant at the lunar poles, potentially as much as 600 million metric tons, and in particular within the so-called permanently shadowed regions, or PSRs, a term that you will hear many times in this presentation. Now, this animation shows the sun's illumination of a few PSRs at the lunar South Pole. We define PSR as a topographic depression, like craters, whose interiors never receive sunlight due to the moon's low axial tilt. And because of this, PSRs are some of the coldest places in our solar system, with temperature below minus 100 degrees Celsius. These conditions create cold traps for water molecules as well as for other volatiles. And that's what makes PSRs the target for the upcoming lunar missions in the search for water ice. To recap, we have some idea of where we can find water ice, but not with precision. And we won't know for sure until we send a rover or astronauts to explore the region. And because we cannot see inside the PSRs, we cannot correlate topographic features of the terrain with where we think this deposit might be. So this lack of visibility also makes it very hard for mission planners to design a traverse for lunar rovers, as we don't know where smaller obstacles and hazards might be on the way. And this is precisely what the results of our work is trying to unlock.
So let's journey into one of these permanently shadowed regions. Imagine being inside one of these PSRs. It's extremely dark and it's one of the coldest places on the solar system. So how on earth can we see into these shadowed regions? Well, it turns out that light does actually enter these permanently shadowed regions. It's not direct sunlight, but it's light that's scattered from the surroundings. And with the help of NVIDIA and their 3D ray tracing, we were able to show that for this crater, which is the Shackleton crater on the South Pole, light does actually enter inside the crater, inside its permanently shadowed region, and it's scattered from the rims of the crater. The problem is, if we take a normal image of one of these craters, it's extremely dark. And what we have to do is increase the brightness of this image a long way down until we can start to see features and inside of this crater. The problem is, if we zoom into that image and we look at it, we can see a lot of noise in the image. And this is because of the very low levels of light that the camera is receiving. This is very similar to what happens on your phone. We've all done it. We've taken a photo in the dark and then we've zoomed in and we think it's a great photo, but it turns out to be really grainy and faded. And the same thing is happening on the moon. Here's where we come in. We designed 2 neural networks to remove noise in these images and improve their quality. The first network we call Destripe network, and it removes stripes in the images that we just saw. The second network we call Photon Net, and this one targets the graininess and improves the resolution and removes that graininess look. Together, we call our software HORUS, or Hyper Effective Noise Removal Unit software. What we've essentially done is design night vision for the moon. And here's the result. The first image that you can see is a raw image of one of these shadowed regions. The second is after we apply our destriping network, removing the stripes in the image. And the third is after our photon network, removing that graininess. And you can see, after applying our techniques, we're starting to see features compared to the raw image that we would never see before, things like craters and boulders. We haven't just done it to this image, we've actually done it to many different permanently shadowed regions on the moon.
So you must be wondering now what we can do with these improved images. Well, the most significant application of our work is, as mentioned earlier, is better traverse planning. As you see here, improving the overall quality of the images can enable us to plan in advance, as there is no room for error within the PSRs. As you see here, our little rover, which could not go into the shadow regions earlier because of the lack of information, now equipped with the information based on our results, know in advance where the obstacles, the craters and the boulders are, and can avoid them. Another major application is the ability to count craters within the PSRs with higher accuracy, as you see in this result. Crater counting is significant as it helps us in estimating the ages of the PSR, which in turn correlates to the chances of finding the ice. The age of the PSR also provide valuable information on mixing of the soil within the PSR and the estimates of the depths at which the water ice can be found. We also tried to locate the L-Cross, the spacecraft instrumental in the discovery of water at the North Pole, at the South Pole. As you see here, the green dot represents the crash site, which we know from the radar and the trajectory data. But till date, we do not have any visual imagery that confirms the crash site within the Cabeus crater. So with our results, we tried to locate that. Although we are not 100% successful in spotting a crash site due to the lack of signal within the Cabeus crater, we could still improve on the local crater's features beyond the existing PSR Atlas images. And it would not be overstating that we got closer to finding the spacecraft and the crash site in the visual imagery than ever been done before. Well, right now, space and the moon are viewed as something far away, limited to astronauts and the space agencies. But in future, this will change. One day, we all will be able to go to the moon. Imagine waiting in a spaceport on the moon, waiting for your rocket back home to the Earth. Our work is just a very small step in that direction, in manifesting that vision. But as we all know, sometimes a small step can lead to a giant leap. Thank you.
Great, wonderful work, Moon for Good team. So I'm going to invite our panelists back up here. And for this commentary, I'd love to know what is one word that you would describe this presentation with and why? So to kick us off, I would love to have Scott.
Hey, so one word to describe this?
Yep, one word.
Night vision on the moon.
Cool, we'll hyphenate that. Yeah, we'll hyphenate it. Great, thank you, Scott. And Aaron, what's your word that you came up with?
I think foundational. And the reason I think of that is because of water is the foundation it's a foundational resource for life as we know it.
Great, thank you, Aaron. And Rodney?
So the qualifier that immediately comes to mind to me is, I think, a bit more subjective, and it's inspiring. I think the reason why is because of the way that this whole project was motivated for the peaceful exploration of the lunar surface, which I think is important, as well as the fact that although there's a long way to get there, it could potentially close the loop to support surface missions by robotic rovers. I think that's going to be critically important when we're talking about performing in situ resource utilization. So yeah, I'll leave it there.
Hey, sir, I'm with Rodney in the sense that just imagine what this could do, right? Because we always talk about AI as a tool of science. And these are the kind of tools that the first woman on the moon is going to be using as she's walking around the surface, right? So AI allows her to see where humans cannot see before. And I think, James is talking about, that's what AI does. It's a tool like the first telescope. And by taking the data that she does have, she can then see things that human eyes can't see. And that sort of augmentation makes space exploration just so fascinating now with AI as a tool. And just one example of what happens when you take that power of, which we use in Silicon Valley and you put in the hands of these genius scientists, and we're starting to see some of that magic happen here today.
I couldn't agree more. And I also feel like your work has been very inspiring. And so I actually am going to have us watch a very inspiring video that our partner Google Cloud has produced on featuring the last year's Moon for Good work as well to end out this session. So please play that video.
I think I always have been looking at the sky, especially the moon. We're going back to the moon. The idea is in 2024, the first woman and the next man on the moon.
You said on time, I think.
This time we want to stay on the moon. We want to have people on the surface that live there, that work on the moon. You can see the moon as a stepping stone for us to go to other places in the solar system. Our challenge was, if you want to build a base, you want to have metal to build structures. FDL is a unique opportunity to bring together scientists, and we have these 8 intensive weeks where we just sit down and work hard every single day. A sprint is a science sprint, if you want. Our goal is to create a map of the moon that tells us potential locations of metal, which we could use for our base in the future.
We use data from 6 different spacecraft. By combining these data together, we create a new powerful data set for machine learning-based anomaly detection.
As we combine data from spacecraft, 42 different layers, that sums up to about 35 terabyte of data. We basically drown in data. And if you want to crunch these numbers, you need big compute, and that's where Google Cloud comes in. We were able to build our own machines with 200 CPUs or more. Intel provides these CPU cores that Google Cloud uses. And what we did in our project is to collect all these maps, stack them on top of each other, basically creating a massive database. We could spend years and decades to try to understand the data, but thanks to the AI and machine learning, we can tell us the answer in a couple of days. We can actually understand the data with labels that tell you, here might be metal, here might be metal, here's probably no metal. We can achieve amazing results.
Hello, my name is John Kalantari, Assistant Professor at the Mayo Clinic, Department of Surgery, and Center for Individualized Medicine. One of the many uncertainties associated with spaceflight is the initiation and progression of cancer. Molecular alterations are pretty ubiquitous in spaceflight, and they magnify the risk of cancer mortality and morbidity during long-term missions. An example of this is radiation exposure from solar particle events and cosmic rays, which are only a few of the many possible causal drivers of cancer that present a significant health concern for astronauts during interplanetary and future Martian surface missions. Now, by understanding the molecular basis of cancer development, we can better assess the impact of various risk factors on astronaut health and either treat, or better yet, prevent cancer before it arises. The problem is, traditional predictive models only get us so far in allowing us to model what has been seen in our observed data sets. Now, in order to generalize beyond our data and account for the known unknowns of cancer biology and spaceflight, we need to start building new methods of causal reasoning that underlie our predictive models. And to address this gap in knowledge and methodology, the Mayo Clinic is proud to partner with NASA and Google Cloud on the Frontier Development Lab Astronaut Health Challenge. The focus of this year's Astronaut Health project is on the development and application of causal inference methodologies for enhancing our knowledge about the true causal mechanisms underlying cancer evolution. So without further ado, please welcome the 2020 Astronaut Health team.
The human race has always wondered what lies in the universe beyond our planet. In a matter of decades, we will be able to send explorers on the first long-duration space mission. But these pioneers of space exploration will be exposed to extreme conditions. This exposure puts them at a higher risk of cancer. On Earth, cancer touches the lives of millions of people every day. Cancer is not just one disease, but many diseases. And to save lives, we need to build a framework to understand the causal drivers of cancer. A causal inference framework can enable us to pull back the curtain on these complex systems, to understand the mechanisms underlying the most elusive biological and medical challenges that we face. To enable us to break out of our planetary bounds and explore the universe that we inhabit, and to aid us in the search for life beyond our planet.
Welcome, everybody. We are the Astronaut Health team, comprised of machine learning and astrobiology wizards from around the globe. We have 4 researchers, Kia Kazili, Adrienne Horfrost, Arno Blas, and myself, Samuel Budd, as well as our 4 fantastic mentors, John Kalantari, Graham McIntosh, Frank Sobochensky, and Kritika De Silva. And over the past 8 weeks, we've been tackling the problem of deciphering the causal mechanisms that underlie cancer. Now, understanding cancer poses 3 unique challenges. Firstly, we have high dimensionality. Cancer primarily occurs due to malfunctioning cells that can exhibit mutations in potentially any combination of the 6.4 billion base pairs in the human genome. And this vast problem space makes the dimensionality of our problem absurdly high. Secondly, the available data sets are very small. Despite the 17 million new cancer cases every year, the biggest consistent cancer data sets typically have fewer than 100 samples. The final challenge is to move beyond finding correlations and to find the true causes or causal drivers that underlie complex biological systems such as cancer. But what does it mean for one thing to be a causal driver of another?
Going back to basics, let's consider the chicken or the egg problem. We can observe millions of chickens and millions of eggs, but this tells us very little about which came first, and whether the egg is a causal driver of the chicken or vice versa. When we start thinking about biological systems like cancer, the questions become a little more complex. Suppose that we find that a mutation to a gene X is frequently observed together with some cancer subtype Y. We might ask, is a mutation to gene X the cause or the effect of that cancer subtype? Or could both be the effect of a third unobserved variable Z, for example, exposure to high radiation? Naturally, there are many such questions that need answering to understand cancer. The importance of unraveling the causal drivers underlying cancer cannot be overstated. By doing so, we can not only develop better treatment strategies, but for the first time, know where to intervene to prevent cancer before it takes a foothold. Acting in this endeavor, we've developed a causal inference framework that is robust to the challenges of biology and cancer. We're proud to introduce CRISP, the Causal Relation Inference and Search Platform. We've developed an ensemble of causal inference methods, from classical approaches to state-of-the-art causal machine learning methods, leveraging the strengths of each to create a virtual petri dish capable of finding causal relationships in extremely complex heterogeneous data. It's designed to be flexible and modular, so it can discover the causal drivers for not just one, but potentially thousands of effects. All that needs to be done is to select the effect to be explained and to provide the data containing both the effect and the potential causes. CRISP then provides the results in user-friendly visualizations to our Streamlit front-end app. We've gone even further and ensured our framework can scale up to the demands of high-dimensional data and multiple queries. Using the incredible resources provided by the FDL and its partners, we're able to ask not just one question, but thousands, and to keep asking questions iteratively until complex biological mechanisms are deciphered. And this is only a prototype. It's ready to be extended toward any stakeholder's desires. So let's have a look at CRISP in action.
As our first use case, we have partnered with the Mayo Clinic to unleash CRISP on the world's largest multi-omic colorectal cancer dataset. Using our interactive front end, we can explore our dataset to build a better understanding of our data. Once our experiment has completed, we can interact with the results to view the predictive performance of each of our methods and analyze their suggested causal features. We can dig deeper into the results and consider how these methods have performed as an ensemble. Here, we can see the combined output of CRISP, view the top overall suggested causal drivers from our ensemble, and use these to deeper understanding of the true nature of the system under the virtual microscope. Of course, it is vital that we validate our findings. However, with the lack of ground truth for our data, this in and of itself is a challenge, which we're overcoming in two ways. We found an overwhelming overlap between suggested causal features from our framework and the efforts of the wider cancer research community. This corroboration of results gives us confidence that CRISP can extract relevant causal features from high-dimension, low sample size, complex biological data. But we haven't stopped there. We've conducted extensive experiments in synthetic data that mirrors properties of complex biological data to validate that CRISP has taken us beyond correlation to extract causal drivers and to develop deeper understanding of each of the methods in our ensemble.
So, in summary, what's new about CRISP compared to previous data-driven cancer research? Well, firstly, we put the focus on causation rather than correlation. This means that in addition to getting an indication of the direction of cause and effect, we're also less likely to identify spurious correlations as causal and more likely to select actual causes as causal. Furthermore, CRISP is a fully modular and easily deployable tool that can help researchers around the world to advance their cancer or biological research. Our code base will be made open source, and it is in fully Dockerized form, making it convenient to run on any data, on any system, at any time with just a few clicks. So we would like to invite you and take a step forward with us, imagining the year 2035. Imagine the first crewed mission to Mars taking off, with the astronauts knowing they're safe from cancer, as its occurrence and development have been fully understood and can be prevented. Imagine the up to 17 million lives per year that will be saved here on Earth. We believe that this vision can become true, and that we should all endeavor to make that happen. We hope that automated causal discovery guided by CRISP can help us all to achieve it. So we would like to thank you all for joining in today. And at this point also would like to thank again all our partners around FDL for making this research possible. Thanks.
Thank you, Astronaut Health Team. And I'd like to go ahead and invite our panelists back. So this time I'd like to know from each of you, what are the implications of this remarkable work that this team has done? And so to get us started, I'd like to turn this over to Aaron.
Yeah, that's remarkable implications. We could, for the obvious, definitely extend this knowledge to cancer populations across the Earth, but particularly the implications would be greatest felt in low-income countries.
Great. Thank you, Aaron. And now I'd like to turn it over to Rodney.
Thank you, Sarah. So yeah, there are obvious implications here. This is moving, I think, the needle of the recruitment of AI/ML techniques to support dual use, what I like to call dual use capabilities or technologies. So clearly, crew members who are going on long duration space flight excursions are going to be exposed to environments which make them a bit more vulnerable. But the fact that we can actually close the loop back to inform how potentially, those insights can support terrestrial diseases of a similar or the same nature is extremely important and valuable. So that's one of the clear implications, and one of the reasons why this particular challenge, among others, I think is particularly well suited to be able to address those for cancer and a lot of other terrestrial diseases.
Wonderful. Thank you, Rodney. I couldn't agree more. And Scott, to close us out.
Hey, Sarah, what I love about this work is that, it's a hard problem. How do you know this, the sources of a cancer? We have this not only for the space exploration, but here on Earth. And what they've done here is they've married AI with fundamental how we do cancer research, the science of that, and they're making it as easy as ordering like a crispy chicken sandwich at Chick-fil-A, right? The idea is that if you have that kind of tool, if it's that easy and that accessible, imagine what all the scientists can do in all disciplines. And I certainly would I like to see Crispy right on the launch pad with them as they're going the mission and help understand what are causal effects, because the mathematics is so complicated for the uninitiated. But to make it that accessible, I think this is the sort of trend we're seeing in tools. We can really, as a race, start to the human race. How do you put together these great tools with the human mind and do things we could never do before?
Thank you, Scott. Yes, I think accessibility is key from the work that this team has done. So with that, I'd like to say thank you to the Astronaut Health team and thank you to our panelists. We're going to go ahead and move over to our two Heliophysics teams. And to introduce them, we have our star, Lika, and let's go ahead and roll that video.
Hi, I'm Lika Guhathakurta, heliophysicist at NASA headquarters. What if you woke up one morning and found your whole planet had been swallowed by the atmosphere of a star? You get out of bed, look out the window, auroras are dancing along the horizon, dark sunspots crackle overhead. Each little pop, more powerful than a nuclear bomb. On TV, a weather forecaster warns astronauts a solar flare is sure to erupt, although he can't say exactly when. Moments later, the satellite signal begins to flicker. Where is this place? Welcome to planet Earth. Yes, it is true. We live in the outer atmosphere of this star. Sun's fiery nature, along with the tremendous gravitational pull, an extensive magnetic field helped it to become the heart of our solar system. Magnetism describes virtually every feature on the sun, from sunspots to the soaring structure you see in the movie on the right. On the right, the movie shows numerical simulation of solar wind disturbances impacting Earth's magnetosphere, which is quivering and shimmering like a cocoon. Study of heliophysics involved three forces, their interactions: pressure, gravity, and magnetic fields. Magnetism being the most critical one, and you'll hear about this more and more. Heliophysics is a relatively new science. It's a unique hybrid between meteorology and astrophysics, and it is also known as the science of space weather and climate. Predicting a coronal mass ejection propagation from the sun to a planet requires a whopping grasp of physics spanning 19 orders of magnitude in time and 25 orders of magnitude in space. Just think about that, involving interactions between multiple layers of the sun's atmosphere, the planet's atmosphere, and the interplanetary medium at both microscopic and macroscopic level. It is hugely complex. In the next slide, I try to show the CME impact and societal consequences of solar variability. Of course, there is human radiation. We have space stations, space exploration and utilization going on full swing, high altitude flight and aviation and aspiration of space tourism itself. ISS is located inside Earth's magnetic field, so it enjoys a degree of protection right now. But future astronauts en route to the moon and Mars will be outside this magnetic bubble, and their spaceships are going to be in direct contact with the sun's atmosphere. Impacts on technology, another one. This could be a multi-trillion-dollar impact depending on the technology sector. Space systems, communications, navigations, ground infrastructure like power grid. More than 500 active satellites circle the Earth, and we are adding to it every day. We rely on them for TV, telephone, internet, GPS, navigation, and weather forecasting. All are vulnerable to space weather. And of course, let's not forget terrestrial climate, both short and long term. The next slide literally kind of describes the domain of heliophysics as the heliosphere itself, which stretches from the bright core of the sun to the dark void 5 billion miles beyond Pluto, where the sun's magnetic field piles up against the plasma clouds of interstellar space itself, the domain of astrophysics. But in the next slide, let's think about it more. It's just not solar magnetic field that's important. A planetary magnetic field makes a difference too. On the top panel, what you see is that Mars, we believe, lost its global magnetic field, removing the planet's main source of protection from solar wind. So Mars's atmosphere is getting pummeled by about 1 million miles per hour solar wind, traveling almost 0.15% the speed of light. This provides enough energy to the particles to escape Mars's gravity. Mars presently loses about 100 grams or a quarter of a pound of atmosphere every second. And this number goes up by a factor of 10 or 20 during a solar storm. In the lower panel, of course, I'm talking about, our hunt for habitable exoplanet. And what we are showing there is a simulation using models developed in heliophysics to show a red dwarf with large spots, rapid spin rate, and deep convective zones that's supercharging its space weather environment and causing the nearby exoplanet's atmosphere to strip off, affecting the ability of a planet to support life. That's what we do in heliophysics. Ultimately, in the final slide, I give a picture of the heliophysics ecosystem as seen from the lens of FDL. So remember, we've been doing this for 3 years, and heliophysics is a unique hybrid between meteorology and astrophysics. Continuing on that theme, our meteorology topic this year is tracking geo-effectiveness of solar storms with multidimensional data and space situational awareness. And the question, can we use ML to understand and forecast complex impact of solar storms on terrestrial technological systems, as I just showed? Or could we use ML to improve our ability to globally monitor geomagnetic storms? On the astrophysics side, the question becomes, can we extract stellar features from exoplanetary transits for understanding, forecasting, and prediction of these exo worlds? And the question, can we use applied AI and machine learning tools and processes to Kepler and test data to identify and define the properties of star spots, stellar rotation, and stellar magnetism in tens of thousands of stars, and both increase our understanding of our own star sun as a star and inform the habitability conditions created by that host star. Thank you, and I'd like to pass it on to the teams to talk about their results now.
Thank you. Hello, this is Bashi from Geo-Effectiveness team, and here I'm along with my teammates, Vishal from India, I'm located in Boston, and Theo in UK, and Panos in Greece, and our amazing team, Asti, Mark, Ryan, and Sida, located in California. We always say sun never sets on our team because we cover all over the globe. Have you ever been in a blackout? Now imagine a blackout, a train signal failing, an oil pipeline catching on fire, communication disruption all at the same time. Each one of these can be caused as a result of the interaction between the sun and the earth. Most of the time, this interaction manifests itself as the beautiful northern lights, or known as the auroras. But sometimes the sun has solar storms and emits bundle of the plasma known as coronal mass ejection. And when they encounter the Earth magnetosphere, they change the configuration and they can induce currents to the system. These geomagnetic storms are not rare events. In fact, they happened many times previously on the Earth. But we were lucky that the most of these extreme cases to date occurred during the time that we were less dependent on technology. For example, Carrington event in 1859, during which the telegraph system, the only technology we had back then, was in fire, and aurora was observed as south as Cuba. And in 2012, we had similar coronal mass ejection, and our satellite, the Stereo 8 around the sun, was able to detect that. Thankfully, it went ejected in the opposite direction of the Earth. But imagine if it faced the Earth. The National Academy of the Science estimated that if that CME faced the Earth, it would have devastating economic impact on the Earth. So now the big question is, can we be prepared for such geomagnetic storms?
The answer is that yes, we can. Just as we produce space weather forecasts, we can also produce space weather forecasts based on measurements of the solar wind and the magnetosphere. But the challenge is that the disturbances start out on the sun, 94 million miles away from the Earth. The solar wind conditions are measured at a single point between the sun and the Earth, and we finally observe the effect sparsely on the ground after the information from the solar wind has been heavily processed by the magnetosphere. Our task, and the overarching problem, is to connect this complex set of dots we have between the sun and the Earth. We have some models to do this, but they struggle with predictions at the scales industry requires. For example, physics-based magnetohydrodynamic models can be used to forecast the magnetospheric response to the solar wind, but they do not reproduce the small-scale structures that are important on the ground, and they are also limited by the fact that they approximate the physics. There also exist statistical models such as the Weimer model, based on averaging geomagnetic measurements and the solar wind data. However, this does not provide a dynamic forecast and only produces a statistical representation of behavior. How do we bridge this gap? We have created a data-driven model that includes a large set of solar wind information that can be used to dynamically forecast the large-scale geomagnetic activity. Additionally, we have developed a set of models to investigate the latitudinal information propagation, laying the groundwork for better localized space weather predictions. I'll now hand you over to Vishal to talk about our first model.
Thanks, Theo. Our first model is what we call the global model. There are two parts to the model. The first part is a global reconstruction model, and the second is a forecasting model. We have seen how geomagnetic activity measurements are not available all over the Earth. we have them only at selected stations where the locations of the stations are present. To combat this sampling issue, we summarize the data at each time step across the globe through spherical harmonic fitting using compressed sensing methods. Essentially, we lasso out a set of sparse coefficients from the measurements. We then consider various solar wind parameters averaged at multiple timescales and feed them in through a groove cell, which sort of summarizes the input into an encoded state. And we then have an MLP, which decodes this information into spherical harmonic coefficients. Once we have the coefficients, we can reconstruct a global map of the geomagnetic activity. And if we sample at the locations where we have stations, we know what the geomagnetic activity at those locations would be. So what do our predictions look like? Hold on to any nuance. And next. You can see the predicted activity on the left, the target on the right. The top row shows the activity over the whole globe, and the bottom row shows the activity at selected stations. You can see from the top row that majority of scales are captured very well, and the global features are captured really well by our model. From the bottom row, we can see that at the location of the stations, the activity is captured pretty well, as in the colors are same. And now we can ask a question: can we understand how activity progresses spatio-temporally using machine learning? I now hand over to Panos to answer this question.
Our second task is to determine whether we can use information from various stations on Earth to better predict fluctuations on different locations. Starting from a physics-driven hypothesis that the effect propagates from north to south, we conduct an experiment to demonstrate that we can indeed forecast locally in the south using data from various north stations. We feed the solar wind data and data from multiple stations into two separate recurrent neural networks to capture the effect and the cause at different locations on Earth. The output of the recurrent neural networks are then fed into a multi-layer neural network, which outputs 30 minutes forecasts of a target station. It's important to note that past information of the target station is not part of the input. Therefore, we're forecasting the effect on a different location than the input data. That way, we measure how the performance improves by incrementally adding information from stations that are more north than the target station. We observe that as we add more stations that are more north than the target, the forecasting performance improves, suggesting that the information of these stations contain effects that are observed on the target at later times, therefore allowing us to construct a better forecasting model for a station location that we might not even have data from. Overall, our contribution can be summarized as follows. We want to increase our ability at forecasting the solar wind effects on Earth as space weather impacts our large-scale and technological infrastructure. Improving our forecasting abilities helps us employ mitigation strategies. With our work, we provide an improved representation of the global geomagnetic activity structure, but also we demonstrate a new methodology for studying information propagation across the globe. Continuing forwards, we aim to improve our forecasting models by providing more localized forecasting, but also build a surrogate model of the heavy numerical simulation models, motivated by the success of our initial results. Finally, we aim to expand our dataset to cover geomagnetic field perturbations at different altitudes. For example, by using data from other missions like Ampere, Swarm, or future constellation satellites like ones from Amazon and SpaceX. We would like to thank our stakeholders, mentors, and FDL team for providing such an opportunity for us. Thank you for listening.
Thank you so much, Geo-Effectiveness team. And I'd like to invite our panelists back to be able to provide a little bit of commentary on your work. So for this round, I'd love to know what's one thing that stood out for you from this presentation. So to start us off, I'm going to go to Rodney.
Yes, so the one thing that immediately stands out to me for this team is that the really compelling results and visualization that were presented as part of this, I think is shaped by the fact that you're pulling from a diverse set of disciplines. You're really calling from the marriage of folks who have expertise in this particular application area, as well as AI ML expertise. And if you're working in either in those disciplines independently, you can only get but so far. When you bring those sort of the intellectual capital that both of those, the people who sit in those different disciplines together and rely on AI, ML expertise and when to use and how to use, first methods based upon first principles in physics. I think that's what's ultimately going to allow innovation to happen. You're operating at the creative boundaries of your discipline rather than at the centers of it. And so that's really what stood out for me, at least, for this particular team, to move us towards hopefully predictions that have a high level of accuracy. Yeah, I'm really encouraged by this.
Thank you, Rodney. And Scott.
Sarah, I think it's echo what Rodney was saying too. I was struck by one thing. Those visualizations were awesome. I mean, I think what they did is such a great job. And I immediately reminded of two things. One, remember Christopher Columbus? And he's exploring. Imagine what he had, if he could actually predict weather. That'd be pretty amazing, right? And I think now we're going out, we'll say we send 30 of these starships to Mars in the next decade, right? It'd be certain, I bet this would be a morning forecast, and I see their visual right there, and everyone's tuned to their version of television, watching what's happening with the weather that's happening in space. And the second thing is here on Earth, we're all trying to connect the next billion. There's a couple billion minds that aren't yet able to access the internet. And that's going to be largely through satellite. And with thousands of satellites, we need the ability to forecast weather. Super important.
Great. Thank you, Scott. Yeah, maybe we'll have a space weather channel for our astronauts in the future. So thank you. And now we have Aaron, you're up. Oh, Aaron, we are unable to hear you. All right. Bill?
So while we,
yeah.
While we wait for Aaron to reconnect, just building on what Scott said and what Rodney said, this kind of work really could become like a dashboard item, as Scott was mentioning, like you wake up in the morning and you see the forecast. I mean, this could be literally on the
right on the starship. Yeah,
right
on the starship.
Yeah,
absolutely.
Really fantastic.
Can I have an app for my Google phone, Scott? Can you make that happen?
We'll do. Okay, I'll take that down. And we need to there's a new job, I think, which is a space weather forecast. Right.
Absolutely.
Yeah.
It's really impossible to understate the importance of space weather and understanding it. I mean, no, but if mentioned earlier, right, how vulnerable we are and our technologies are. If a Carrington event happened today, we'd all go dark, and it could be for months. So this kind of forecasting could really prevent that kind of catastrophe. It's really, really extraordinary.
Right, and the physics, Bill.
Bill, that's exactly what I was going to comment on. Yeah, that was exactly what I was going to say. Is hopefully one of the things that struck me was one of the opening comments that was, we can be ready, but I couldn't help but to think, in the middle of a global pandemic right now, is we heard we can be ready, but are we ready? And after seeing this, it's hopefully there's so many policy implications for this.
Yeah, totally.
Thank you so much, Aaron. And so now we're actually going to move over to our next Helio team that's going to kind of go in a completely different direction. And that is our Star Spots team.
Thank you. Hello, thank you for coming. We are the Star Spots team, and I am excited to share with you some of the work that we've been doing over the past couple months. I'm Daniel Giles. I'm a researcher. I'm joined by Tansu, Emmanuel, Lisette, and Stella. Our mentors have been Andres, Brett, Anna, and Siram, and we are so thankful for their mentorship and their guidance throughout the entire process. Let me begin by talking about the sun. The sun is central to our life on the Earth. It affects us every minute of every day. At its most extreme, it can take out satellites, it can take out power grids, leaving us in a state of chaos in just a matter of minutes. But on the other hand, it also sustains and nurtures life through its light and its warmth. And flares themselves may have helped in sparking life on Earth in the first place. For our neighbors like Mars, it stripped away all of those protections which are necessary for life, as we understand it on Earth at least. And understanding the stellar magnetic activity is key to understanding our stellar system. But understanding this magnetic activity requires careful observation. On the Earth, observing the sun, we can take detailed observations directly of the sun in a number of different ways. One of the most informative ways is to observe spots that appear directly visible to our eye. These spots are directly connected to the magnetic activity that's happening in the star. And by studying these spots, how they evolve, how they form, how they go through different activity cycles, we've come to our current understanding of stellar magnetic activity. But the sun is just one star of many billions of stars. Stars at different stages of their evolution, both younger and older than our sun, and which have their own planetary systems. If we can study the spots in even a fraction of these systems, we can gain a better understanding. We can glimpse the past and the future of our own sun. We can understand the habitability of other worlds, and we can understand the physics of our cosmos in a deeper way. I'll pass it to Tansu now to talk about some of the difficulties involved in this sort of study.
Thank you, Daniel. So space telescopes such as NASA's TESS and Kepler observe the brightnesses of thousands of stars over extended periods of time. And these one-dimensional time series are called light curves. And it is important to note that space telescopes do not spatially resolve the stars of interest here. In this context, our purpose is to use these data to infer stellar spots on thousands of stars other than our sun in our galaxy. This is a hard inference problem. It is mainly because a given light curve can be explained by many different combinations of spot multiplicities, locations, and sizes, as illustrated by the colored light curves here. And please do note that spots at different latitudes rotate at different velocities. Existence of more spots on the star just makes the problem even harder. And in addition to this degeneracy, the supervised learning or supervised machine learning problem is very challenging because there is very little ground truth information available. And given the large amount of data on these stars, the problem is inherently computationally expensive. Next, Emmanuel will talk about our methodology.
Thank you, Tansu. So we approach this problem from two different directions. For the first direction, we use a physics-based model, fully probabilistic. So we have prior distributions over stellar and spot parameters. And we try looking for posteriors from the real data, distributions over parameters that best describe the data. Now, doing inference on this problem is difficult. So to combat this, we do a two-step solution. It's robust, where we combine state-of-the-art and traditional methods in order to get the best posteriors possible. Even with scaling, inference can still be quite slow. So for the second direction, we also decided to go with a data-driven approach using supervised learning and using neural networks based on ground truth from real data. Not to reinvent the wheel, we decided to take state-of-the-art methods from well-known machine learning algorithms. And in order to facilitate this, we had to come up with different time series to image transformations that capture time correlations and distances and other features. And in doing this, we were able to regress single parameters given light curves. It's a neural network, so naturally it's much faster and much more scalable. So now we have this synergistic framework, which we call the starry spotter pipeline, which is the best of both worlds. You take the fully Bayesian physical model, and then we take the fast scalable machine learning model, and together they cover each other's strengths and weaknesses so that we can get the best of both worlds. And now Lisette will explain the results of our efforts.
Thank you, Emmanuel. So here on the left, you can look at the excellent fit between our Monte Carlo model and the light curve data. And on the bottom, you can see how this probabilistic approach allows us to have a tight distribution of posteriors. That means that we can constrain stellar parameters such as the rotational period, the inclination of the star, and also the shear coefficient, which is key in differential rotation and understanding stellar magnetism. We can also find this distribution of parameters for spots themselves, such as their sizes and their location on the surface of the star. This method is quite compute intensive, so we can apply it to a few stars for now. And this is why we rely on supervised learning to tackle the data in a different way. So in supervised learning, we're taking advantage of this transformation of the time series into images in order to apply our convolutional neural network to thousands of stars. On the left, you can see how highly correlated our predictions for the rotation period for thousands of stars are to the ground truth, which is a previous study on these same stars. We hope to scale this up to many more stars in the future. And now for some final thoughts, here is Estela.
Thank you, Lizette. So we know light curves are highly degenerate, and before we used to have a very scarce ground truth, because obtaining ground truth is usually very computationally and observationally expensive. But now we have our stereo spotter pipeline, and with the probabilistic forward model approach, we were able to work not only with the rotation period of a star, but with the other parameters that describe star spots. We were also able to constrain the physical parameters, generating a currently growing ground truth dataset. Moreover, with our supervised learning approach, we were able to speed up the process. So we have now a pipeline, we have laid down all the foundation, and we are ready to get deeper in star spot studies in a scalable way. So our take-home message is we are the star spot team, and we want to understand star spots. And we have a big challenge: disentangling signature of a spot from the light curve of a star. In only 8 weeks, we combine different models to constrain spots and stellar parameters on thousands of stars. Our next steps are to evaluate the uncertainty of our methods and apply them to many more stars, contributing meaningfully to the studies of stellar magnetism. So thank you, and a special thanks to all of our partners and external advisors.
Great. Thank you so much, Star Spots. That was really wonderful. And I'm going to invite our panel back up. So this time I'd like our panel to either give one word or one sentence about what does this work with their starry spotter and the work they've accomplished make possible. And to kick us off, please, Scott, you're up.
I would simply say scalable star spots for the win in astrophysics.
Great. Thank you, Scott. And Aaron?
Yeah, just kind of the obvious physical and rotational understanding.
Thanks. And Rodney?
So one word, transformational. The fact that you're faced with a lot of challenging circumstances and you could transform them into actionable information that actually is explainable and accessible to a broad, diverse set of folks is, I think, pretty impressive.
Great. Thank you, Rodney. And thank you to our panel and to our Star Spots team. To close out our Heliophysics section, I'd like to wrap up with a video from Google Cloud that highlights the work of the previous FDL. So if we can please play that video.
The sun gives us life. Without the sun, life on this planet would not be possible. We spent so much time looking really far into the universe, but our own star, the sun, is right there, and there's so many things that we don't understand about it. The sun is incredibly dynamic, and there's a number of processes that go on the surface. And Some of them can lead to particles being ejected into space. And when these particles travel to us, they can interfere with communication systems, with GPS systems. They can destroy our satellites and our power grids, which means we're going to be sitting in the dark. What my team is trying to do is we have images of the magnetic field of the sun for the past 50 years. The images that we have from back in the day are significantly lower resolution than the images that we capture today. And we're trying to use machine learning to increase the resolution and make them higher quality, to understand how we might be able to tie that in with effects that we're seeing here on Earth. We have millions of images that we're sending through a network that we're trying to get something useful out of. Without Google Cloud and Intel CPUs, none of this would have really been possible because we wouldn't have had the computing power and we probably would have waited for a whole year for our models to train. But instead, with one click of a button, it takes us 5 minutes and then our model is done. In a world where we're so reliant on satellites for communication systems, but also we need to understand exactly what makes us vulnerable. I really hope that in the future, scientists will make more use of machine learning to have computer scientists and natural scientists working together on solving the world's biggest problems.
Hi, everyone. My name is Pina, and I'm a Deputy Program Scientist in NASA's Earth Science Division. In NASA's Earth Science Division, we study nearly everything in the Earth system, from the top of the atmosphere to deep underground, including oceans. NASA's Earth Observing System Data and Information System, which stores data from Earth-facing satellites, has over 33 petabytes of accessible data, or equivalent to 67,200 years of uninterrupted MP3 music. Artificial intelligence and machine learning are useful to help extract patterns and knowledge from large data sets that will accelerate our geophysical understanding of Earth's processes. In one project I would like to introduce, we have the Earth Intelligence Engine project being led out of MIT. This project uses machine learning to generate photorealistic images of coastlines after flooding, especially from a tropical cyclone. A project like this is of particular interest to emergency managers from the federal to local levels. This is also of interest to programs at NASA, such as the Disasters Program in the Earth Science Division. In another project I'm introducing, we have a lightning study being led by partners from Lockheed Martin. This project uses data from a lightning sensor on a satellite 36,000 kilometers away. This is the equivalent to starting in Eastern Africa and going all the way around the globe and ending up in Western Africa. This geostationary satellite is fixed on looking at North and South America, as well as the Atlantic Ocean. Understanding how lightning impacts severe storms can help improve the predictability of storms. This type of work is of great interest to communities across the globe impacted by severe weather. So without further ado, I'd like to introduce the teams.
Hello, everyone. We are the Lightning and Extreme Weather team. The 4 researchers on our team are Yvonne, Merrick, Nadia, and myself, Maria. Our 4 team members or mentors include Mark, Clem, Samantha, and Greg Renard. We would also like to acknowledge Benny, Adwait, and Greg Sine for their contributions to our work. During the evening of April 22nd, a tornado moved across Southeast Texas. This tornado had maximum winds estimated to be 130 miles per hour, lasted over 45 minutes, and carved a path of destruction 37 miles in length. The damaged path was so substantial that it could be seen from space. Here's an image of that path. Severe thunderstorms can produce hazards that include tornadoes and large hail, which can claim lives and cause substantial economic damage. The cost associated with the cost and societal exposure associated with severe storms has been increasing in recent years, and this makes it that much more important to continue improving our understanding and predictions of these storms. During severe thunderstorm events, forecasters are under pressure to issue warnings that can alert the public of imminent danger. Forecasters have a large amount of physical model output and observational data to analyze, but very little time. Now, Merrick will introduce how our project aims to help forecasters.
Our challenge is to use geostationary satellite observations for short-term predictions of severe weather. Forecasters ingest an enormous amount of information and utilize their domain knowledge and experience to issue warnings. We aim to build a tool that can help forecasters identify the storms with potential to evolve into tornado or hail hazards to increase forecasters' situational awareness and be more confident in their assessments. With the recent launch of the GOES weather satellite, the geostationary lightning mapper, an optical lightning sensor, shown here on the left, now offers unprecedented continuous coverage of lightning across the Western Hemisphere. GLM captures 500 frames per second and sees about 1 million lightning flashes per day. Lightning occurrences anywhere across the full disk of Earth are then downlinked in nearly real time. Since lightning is a proxy for the intensity of thunderstorms, we ask the question, with the wealth of lightning observations from GLM's unique vantage point, can we use state-of-the-art machine learning techniques to skillfully forecast tornado and hail hazards? Ground-based observations of lightning have shown the utility of lightning data to aid in predicting severe weather events. In many cases, like the time series shown here, there is a spike in the lightning rate prior to the onset of a tornado or of hail. As updrafts become more vigorous, more charge separation occurs, which leads to more lightning strikes. Next, Nadia will talk more about how we use the lightning data from GLM to make predictions.
To accomplish this, we used 31 nodes to process millions of files of GLM lightning events from March 2018 through June 2020. Each file spans 20 seconds and covers the full disk of the Earth observed by the GLM. We derived several physical quantities and gridded the data into 2 kilometer by 2 kilometer bins at a 1-minute cadence. We then focused on the Great Plains of the US during the spring of 2019, where many severe events occurred. Our approach to this problem was to exploit lightning behavior leading up to severe weather events temporally as well as spatially. From the temporal aspect on the left, we transformed lightning time series such as flash rate and flash area using 10,000 random convolutional kernels, Rocket, to extract features in a single layer, which we fed into a classifier to determine the severity of an event. Spatially, as seen on the right, our approach utilized computer vision on the lightning data, augmented by cloud top temperatures from another co-located instrument on the GOES, the Advanced Baseline Imager. Spatiotemporal patterns were then examined using video frame prediction techniques based on recurrent neural network structures embedded within a two-dimensional ConvNet architecture. While some initial results are shown, I'll hand it over to Yvonne to discuss the results of the GLM time series classification.
We use two well-known metrics in the atmospheric science to assess the skills of our models: the critical success index and false alarms ratio. Both metrics are defined based on the 2x2 confusion matrix or contingency table. In the table on the right, we can see the skill of our model paired to the state of the art by the National Weather Service. Our results are very positive, but we must note the differences in lead time, coverage, and period. To summarize, our results are the following. We built a model with 15-minute lead time using 8 GLM quantities. In our test data sets, the false alarms for warm storms with no actual severe weather reports were reduced by 50%. In addition, in 8 out of 10 times, the model was able to classify the severe weather correctly. These results suggest we can continue to enhance and refine this work to help forecasters using lightning data. We aim to have these models tested at the NOAA Hazardous Weather Testbed in Norman, Oklahoma, firsthand by forecasters.
The April 22nd tornado of Southeast Texas moved across a rural area, so there were no serious injuries. However, we may not be as lucky with the next tornado. With GLM data and machine learning, however, we can be prepared. We'd like to take the time to extend an expression of gratitude to those who believed in us, to the Frontier Development Lab, to our mentors, and all of the key contributors to this project. Thank you for giving us the opportunity to make good science with great impact. Thank you.
Great. Thank you so much, Lightning team. This was really exciting work. And I would like to bring out our panelists once again. So this time, I'm going to ask our panelists if they can tell us one sentence about why this is important. And to start us off, I'd like to turn it to Aaron.
Yeah, so the average lead time for a tornado warning is about 13 minutes. So with this project, like this, can we improve the predictability of severe storms?
Thanks, Aaron. And now I'd like to turn it over to Rodney.
Well, this one hit home for me, having family that lives in basically hurricane vulnerable areas. And certainly having any additional lead time will be instrumental in effective in trying to take cover. The fact that the team is actually focused on false alarms and misdetection, as I think is extremely important too, because false alarms and false negatives have dramatic implications as well.
Thanks, Rodney. And Scott?
Sarah, I almost felt I was watching weather forecast again. But what's interesting here is that you've got the atmospheric sciences. Now you blend that with sensors from NASA and new sensors from NASA, as well as the science of Silicon Valley. And those two together are doing things that in a few years we'll expect to see forecasts for where lightning and storms will be happening, and hopefully get ahead of those terrible things we talked about, that long stripe that took out all that area in Texas. So I really look forward to them bringing this back into mainstream, see it on broadcast TV.
Yeah, same here, Scott. Colorado has a lot of severe weather, so definitely would love increased warning time. So with that, I'd like to thank the Lightning team and our panel, and I'd actually like to send it over to Deva from MIT to give us a few words. So if you can roll that tape.
Hello, I'm Professor Deva Newman, the Apollo Program Professor of Astronautics at MIT. It's my great pleasure to introduce you to the Earth Intelligence Engine. This is an amazing team that's come up with novel uses of artificial intelligence, using physics-informed neural nets and GANs, generative adversarial networks, all that to paint the pictures to create the satellite imagery of the future. What will the satellite images look like of the future, especially for Earth systems and coastal flooding? Can we paint that picture in order to benefit humanity, get people out of harm's way, look at their rescue, and just understand all of Earth systems? So important for MIT Portugal to sponsor this project with NASA, because we really are very excited about the work that the team's doing to further climate response and understanding Earth systems better by using artificial intelligence. Why is it important to the world? This work is so important for everyone to have a better understanding, kind of put it in your pocket, have ease of access to satellite imagery of the future, especially for natural disasters, and in this case, extreme coastal flooding, the oceans and the land and where our urban populations are, and to show those satellite images using the artificial intelligence and the tools that the Earth Intelligence Engine team has developed. So glad to introduce them to you.
Thank you. According to the UN, flooding is the most expensive disaster in the world. Today, floods cost the US billions of dollars every year, and climate change will only increase the frequency and the intensity of these flooding events. Now, imagine a city planner attempting to convince the city council to fund more climate resilient infrastructure development, perhaps the establishment of seawalls or mangrove protections. So the question then stands, how can this city planner communicate the flood impact most effectively in order to receive the support and the funding for climate resilient infrastructure development? Today's flood visualizations are either informative, like pixels on a map, or intuitive, like street level flooding. And what we gathered from our expert interviews was that the color-coded images can be hard to grasp for non-technical decision makers, and our street-level imagery just doesn't have enough information for decision support. So there is a research gap here. And 8 weeks ago, we set out to fill that research gap. Hi, my name is Oceane Boulet, and I'm a researcher on the Earth Intelligence team. I'm from Florida, a place where hurricanes and flooding come in annual seasons. And I'll never forget the moment when I was 10 years old, huddling with my mom in our bathtub as we waited for a massive Hurricane Charlie to blow over Orlando. That moment made me realize how humbling natural forces can be. That is why I am grateful to have been able to be a part of the Earth Intelligence team, where over the past 8 weeks, we have deployed a tool to ease communication between experts and decision makers when it comes to realizing flood impact. We have leveraged generative vision models to create physics-constrained local visualizations of future flooding on the US East Coast. We do this to assist in climate-resilient city planning. In other words, we can now generate satellite imagery of floods that have yet to happen. Throughout this presentation, I will share with you some of the previous research that we've built upon, how we created the physically constrained satellite imagery, and then how we evaluate that imagery. But first, a little bit of the research work that we have built upon. SLOSH is a physics-based storm surge model from NOAA. In general, the SLOSH model output is not very high resolution, but because many government agencies use SLOSH and we want our work to be accessible by those government agencies, we decided that it was very important for us to use SLOSH as well. What we also need, satellite imagery. And we are glad to have had sources for high resolution satellite imagery, which consisted of pre and post-flood images of 6 disasters throughout the US. Finally, we need a way to combine the SLOSH model outputs with the satellite imagery. And for that, we turn to a new generative vision technique called a GAN, a generative adversarial network. So we begin with a pre-flood image, like the one you see here. We used an unmodified GAN called Pix2Pix HD to add flooding to these images. And we got an image like this one. The problem is this unmodified GAN, one without a physics-based output, so SLOSH, for instance, is just adds flooding in randomly because there are no physical constraints. This generated image is off base, and we see this because the ground truth actually says that our post-flood does not have water where the GAN says we should. In other words, we clearly need to modify this GAN. We need physical constraints. So that brings us to the work that we have done. We have created the first physically constrained photorealistic visualizations of coastal floods. This is a satellite image before Hurricane Harvey hit somewhere in Texas. And this is the same location, but now post-flood. Now I'm about to show you a third image. And if we are successful, then the image I'm about to show you will look strikingly similar to the post-flood image you see. Ta-da! As you can see, they're very similar. So now let's dive into how we got this generated image. Our GAN learned the relationship between a pre-flood image, a segmentation map, and a post-flood image. See, during training, the GAN had access to all 3 of these images, but during inference, we only showed it the pre-flood image and the segmentation map, and we asked it to generate a post-flood image, which it did. We actually ran a few experiments. Just as a reminder, our pre-flood imagery was used as input, and our post-flood imagery, this is what we want our generated imagery to look like. This is the goal. Our initial segmentation map was used as input, and we used it in order to create baseline. So our baseline is essentially takes the pre-flood image and paints all the pixels that are supposed to be water brown. And our GAN looks pretty decent here. We'll go into how we evaluate decent in just a moment. However, in order to visualize future floods, we cannot use high resolution segmentation maps. Why? Well, because these high resolution segmentation maps only exist for past floods. Instead, we hope to leverage SLOSH, which projects future floods. But remember, the SLOSH model outputs are usually low resolution, as you see here. Therefore, our baseline also looks pretty pixelated, pretty low resolution. However, our GAN still does reasonably well. And once again, we will go into how we evaluated these imagery in just a moment. But before that, I would like to discuss the metric that we used in order to evaluate these images. Today, there is not, to our knowledge, a metric that measures the trade-off between photorealism and flood physical consistency. That's why we propose the Flood Visualization Plausibility Score, or FVIPS. LPIPS is a perceptual similarity metric that helps us compare these 2 images, whereas the intersection over union, or IOU, is a metric for how well our predicted segmentation lines up with the actual segmentations from the NOAA storm surge models. By combining LPIPS and IOU, we can now assess photorealism and physical consistency. So now that we've discussed how we've evaluated these images, let's see some results and correlating scores. On average, our generated imagery got a higher FVIPS score than the baseline for all 3 experiments, including the physics uninformed model that we started with, the slosh physics-informed model, and the high-resolution physics-informed model. We constrained generative vision models with physics-based inputs to visualize future flooding, which is what you see in the bottom row of images here. In other words, we set out to help city planners communicate more effectively, more visually, and more intuitively about flood risks in order to support climate-resilient infrastructure development. And we have done that. Going forward, we'd love to see other researchers build upon this work. We intentionally made our system architectural generalizable. We applied GANs to earth science, and we look forward to applying this method to visualize the impact of climate extremes on different geographies, different times, and different disasters. We'd also love to see our work integrated into existing systems and making it publicly available. We could not have done this without the incredible support that we got from both our mentors and our partners inside and outside of FDL. I learned at 10 years old how humbling nature can be. And climate change will only intensify these natural forces. But together, we can build technology that supports a world in which all of humanity is resilient to climate change. Thank you.
Great. Thank you so much, Earth Intelligence Engine team. So I'm going to invite the whole team as well as our panelists back. So for this one, I loved you guys' slider, by the way. I would like to ask the panelists if you guys can share in one sentence what you would like the Earth Intelligence Engine team to work on next. So to kick us off, Rodney.
Well, that was a stellar presentation. One of the things that immediately comes to mind is transferability. How well can using this approach be used in a completely different set of circumstances, and to some extent scalability? I think it's really useful to do a proof of concept. And I really believe, trying to determine how best to deploy this in an operational setting is extremely important, as well as scalability and transferability.
Great, thank you so much, Rodney. And Scott.
A U.S. Association of Insurers believes there's a $20 billion market for flood insurance up for grabs. And what you've shown here is the blend of AI models with physical models that's doing things better than either apart. So I highly encourage you to look at that market, because there's a lot of people who would love to see this.
Great, thanks, Scott. And then Aaron.
Yeah, I would really, I'd love to see the work here applied to future climate projections. It'd be invaluable knowledge to all out there.
I absolutely agree. And I hope you guys continue on with your work. So I'd like to thank our panelists and our team. And to kind of continue talking about floods, I'd like to play a video from our partner, Google Cloud, on last year's floods work.
At FDL, we're bringing together researchers who know a lot about machine learning and AI with researchers who really know the ins and outs of the problems that have a really big impact for the future of humanity. So I'm on the disaster response team. Floods are a really devastating natural disaster that impacts more lives across the world than any other natural disaster. Here in the United States, we're actually fortunate to have this stream gauge network. We have these monitors that tell us exactly how high a river is and how much water is flowing through an area. Based on satellite imagery, can you actually remotely sense how high a river is just by looking at the top-down image? Specifically, we're focusing on tying satellite images to the stream gauge readings and seeing if you can predict the readings from the satellite images. And if we could do that, that actually increases our ability to do flood modeling in areas that don't have these physical stream gauges anywhere in the world that is at risk for experiencing floods. So if we have a model that gives us even a 30-minute additional warning time before this flood hits, in that 30 minutes we can get a family to safety. Google Cloud has really been what's made it possible for us to do our work on a day-to-day basis because of the amount of data that we can process. I think it's a really exciting time to be a machine learning scientist because more and more opportunities are appearing to apply these tools to really exciting problems.
Hi, I'm Rahul Ramachandran from NASA's Marshall Space Flight Center. I manage a project called Impact, focused on maximizing the use of NASA's Earth science data. As most of you know, one of NASA's science missions is to study Earth as an interconnected system using instruments on satellites, airborne assets, and other observing platforms. NASA holds the most extensive data archive of Earth observations. The data archive contains 35,000 different data sets, over 500 million data files, and is growing exponentially. The data archive is open and serves the entire global science community. The goal of the Knowledge Discovery Framework, KDF, challenge is to develop a new methodology for our data users to search this vast archive to identify different kinds of phenomena and unusual patterns in the data. The methodology must be general purpose and work on a wide variety of phenomena and patterns. This new kind of search would go beyond what exists today and potentially serve as a useful discovery tool to accelerate science. I would now like to introduce the team.
Thank you. Hello, everyone. Thank you for coming. We are the Knowledge Discovery Framework team. From left to right on the satellites are the researchers, Satyarth, Megs, me, Francesco, and Nishan. Then down on Earth are our project mentors, Anna Maria, Aniru, and Hesham. Our challenge goal was to create a generalized reverse image search algorithm for remote sensing phenomena. Earth observations, or EO, have revolutionized Earth science by providing data at unprecedented temporal and spatial scales. Yet, imagine searching through 33 petabytes or 660,000 Blu-ray discs of unlabeled remote sensing data for one particular phenomenon. Keep in mind that this number is expected to increase sevenfold at minimum in the next 30 years. So we set out to build a general algorithm that could search these dozens of petabytes of data. So how would such a system look? Let's say that I'm a researcher studying the interplay between hurricanes and dust storms. My first step would be to download every hurricane event within those 33 petabytes of data. While some storms are cataloged, they are few and far in between. Ideally, I would input a query image of a hurricane into the KDF algorithm, and it would search the NASA EO data and return all examples of hurricanes. Then, I could use the very same algorithm to obtain all records of dust storms from a different query image. Such an algorithm will be able to return other phenomena such as wildfires, volcanic eruptions, or even particular cloud formations. So why hasn't this been done before? Well, there are several challenges that hinder generality. The first is the scarcity of remote sensing images which are labeled. Labeling data is typically very time-consuming and expensive. This requires the algorithm to be self-supervised, in other words, without human input. Another challenge is accurately assessing scaling between different phenomena. For example, hurricanes are 500 kilometers across on average, while a small wildfire could be less than 1 kilometer squared. While this problem has been addressed in typical machine learning object detection, it has proven to be elusive in remote sensing data.
Lastly, phenomena might require different spectral bands and resolutions to distinguish events and objects. For example, hurricanes can be detected using a single band of near-infrared, while dust storms require more bands. For other phenomena, such as coral reefs, red, green, and blue channels might need to be supplemented by additional bands. The KDF user-friendly EO similarity search engine requires a robust featurizer. Our featurizer used an image reconstruction autoencoder as a self-supervised convolution neural network. This featurizer will be publicly available and can be used as a base model during transfer learning for developing remote sensing computer vision classifiers. To evaluate our featurizer, we used two test cases: a curated hurricane dataset from GOES and a realistic dust storm dataset from MODIS. Labels were not used while training this featurizer in either test case, allowing us to assess how well our self-supervision network can perform in the absence of labels. The hurricane dataset featured images with hurricanes of different categories. The hurricanes were centered on the image and absent of any sensor artifacts, whereas the realistic dataset represented one region on the western coast of the Sahara and included many artifacts such as no data strips and clouds. Furthermore, land features are often visible through the storms, while hurricanes are not transparent. The dust storms captured in the realistic dataset were often at a much larger scale than the hurricanes. Lastly, the hurricane dataset only used one spectral band, while the dust storm dataset used red, green, and blue.
Okay, so as mentioned, we use image reconstruction autoencoder as our self-supervised module. Since we do not have labels, we cannot have a supervised learning module. So we generate our own kind of labels and have a self-supervised module instead. An image reconstructor autoencoder tries to reconstruct its input image. Autoencoder, by definition, is a kind of deep learning architecture that consists of two subsections. One, the encoder, that transforms the input to the smallest resolution feature vector that Nishan talked about. And second, the decoder, that tries to reconstruct the image from its feature vector. This feature vector is a higher dimensional representation in terms of channels of the image. The reconstructed image is in a way a piece of visual evidence that the features successfully capture the prominent properties of the input image. Now, given that we have our featurizer working, the next question is, how good is our generalized featurizer when finding similar images? Here, we demonstrate our similarity search on a tropical storm image. That is in the top row. The wind speeds are measured in knots. The left image is the query image, and the images to the right are the three most similar images, or the three nearest neighbors according to our featurizer. We can see that for this example, the hurricane featurizer found the majority of the hurricanes of the same category. And even the one that is misclassified comes pretty close in terms of wind speeds. This meaning that the featurizer captured this correlation between the hurricanes in the unlabeled data. We used accuracy at K to quantify how frequently the similarity search finds images within the same category of the query image. The x-axis represents the number of nearest neighbors, or the number of similar images returned. The y-axis represents the percentage of times the nth nearest neighbor returned image within the same category as the query image. For the 5 nearest neighbors, the featurizer had 45 to 90% accuracy, meaning that our featurizer worked well on the hurricane dataset.
But what happens when we test the featurizer on a realistic dataset? The hurricane dataset was an ideal test piece as the hurricane is the only feature in the image. But the dust dataset is a bit messier, as we have other objects within the images, such as continent edges, clouds, and no data strips. As shown in the top row of images, the query image of the dust storm on the left returned images with both dust and no dust. As we can see from the accuracy at K graph below, the featurizer was half as accurate predicting dust storms as it was predicting hurricanes category. In conclusion, we were able to obtain meaningful search results using the same featurizer and similarity search algorithms for two diverse atmospheric phenomena in the absence of labels. The curated hurricane dataset is ideal for testing the featurizer due to its reduced complexity, but it may not reflect the reality of remote sensing data. The dust storm results demonstrated that featurizer accuracy is highly dependent on the appearance of the phenomena and the data quality. The challenges we faced adapting the featurizer to the dust dataset are not unique for this phenomenon. So developing a general featurizer that works without labels will require us to resolve challenges regarding the focus, scale, and spectral resolution of the dataset. The Earth system is undergoing rapid change. Direct and indirect human activities have resulted in desertification, increased intensity of hurricanes, bleaching of coral reefs, and other large-scale environmental changes. Earth observations are a means of studying environmental hazards and can aid in conservation decision-making. Yet those decisions and scientific breakthroughs may be buried in 33 petabytes of archived data. Our general featurizer takes one step towards a robust, user-friendly tool that provides the necessary data to the people who can make the most difference. With that, we'd like to thank everyone for their time and all of the people who have helped support us, especially Raul and the Impact team.
Great. Thank you, Knowledge Discovery Framework team. And I'd love to invite our panelists and all of our team from the Knowledge Discovery Framework back on. So for this round, I'd like to ask our panelists, what is one thing that this search capability enables? So to kick us off, I'll turn it to Scott.
This is at Google, this is the next generation of search, where it's called semantic search. There's far more unlabeled data than labeled data. And these sort of techniques we're actually using at Google and is implications across all kinds of industries for video and imagery.
Great. Thank you, Scott. And Aaron.
Yeah, so as I mentioned, this is 33 petabytes of Earth science data. As the authors mentioned, this is 660,000 Blu-ray discs, or 67,200 years of MP3 music. So this is an exorbitant amount of data. So what it does is it really enables us to bring to light and make sense of all types of Earth science data, from the top of the atmosphere to our deep oceans.
Thanks,
Really
Aaron.
exciting.
Yeah, great. And Rodney.
So the one thing that came to mind here, where I think, what this work can really help to inform and enable is a deeper understanding of a phenomena that I recently, in the past few years, just became aware of, not being an Earth scientist myself, called teleconnections. And I guess it's sort of a term in atmospheric sciences that refers to climate anomalies that are related to each other at very large distances that might otherwise seem unrelated. So really think that, again, a deeper understanding of that whole phenomena could potentially be an area where this work can be brought to bear upon.
Thanks, Rodney. That's a great add. And now I'd like to thank the Knowledge Discovery Framework team and our panelists. This was great. Up next is our last team of the day, the Waters of the United States, otherwise known as their acronym WOTUS. And for the introduction to that team, I'm going to turn it over to John from the USGS. So if we can play that video.
Hi, I'm John Stock. I run the USGS National Innovation Center. I'm pleased that my agency is sponsoring the Waters of the United States FDL Challenge this summer. I'm going to take a few moments to describe the USGS to those of you who may not know us, And then I'll tell you why we think this challenge is so important, not just to us, but to countries around the world. The U.S. Geological Survey was born in 1879. Since then, we've developed the facts and forecasts our nation needs for its lands, waters, and ecosystems. Our maps and data tell an ever more detailed story of our national assets, like our minerals, soils, waters, and ecology, and our hazards, like earthquakes, floods, volcanoes, and landslides. Our nation uses USGS maps, data, and expertise to make decisions about the natural resources that we use to build infrastructure and commerce, and the things that threaten them. The nation trusts our tools because we provide facts and forecasts without advocacy. In short, we provide knowledge for national action. But we have some gaps in that knowledge. One of those gaps is where are our streams flowing right now? Earth's branching stream networks expand with floods and contract with droughts. There's no one map of our streams. But what if we could map these flowing networks every day, stacking the time series maps over many years? Mapping our daily waters gives us an early warning for where droughts are born, the receding tips of the flowing network. Mapping them over years gives us a map of the impermanence of our waters, showing where to expect water and where not to. This would be a fundamentally new map, one that has never been made at scale before, and one that will have huge impacts on water resource use around the world. Today, you're going to see a talented group of data scientists explore our ability to augment human mapping by applying AI to high-resolution satellite imagery. USGS scientists from our water mission, our National Geospatial Program, and our National Land Imaging Program have been working hard over the last months to provide the training data for this effort. This partnership happened because of the generosity of our colleagues at NASA, Maxar, Planet, SETI, and Trillium. I look forward to exploring how USGS will use these models as we pursue the goal of mapping our nation's streams in real time. Thank you.
Hello, and welcome to today's digital showcase. We are the Waters of the United States team, short VOTUS. While we already heard of FDL challenges today related to floods and their effects, one of VOTUS's goals is to assess where such excesses or shortages of water come from in the first place. Our team consists of researcher Dolores Garcia, Gonzalo Mateo, me, Hannes Bernhard, Ron Hagen-Sieger, as well as ML lead Freddy Kalaitzis, super mentor Guy Schumann, USGS contact Jonathan Stocks, domain lead Kevin Dobbs, and ML support Ignacio Lopez. We also want to specifically thank our sponsors, Planet, USGS, Google Cloud, without whose processing capabilities, storage capabilities, and data, this project would not have been possible. The current framework for the mapped US stream network is based on mapping campaigns conducted in the mid-20th century, that is 60 to 70 years ago, and based only on a single set of images. From an ecological, sociological, economic, and regulatory standpoint, more information is needed on the time-varying characteristics and categorization of streams in the network. The VOTUS challenge is focused on using modern methods and a range of geospatial data to refine and update the categorization and characterization of the streams at continental scales. The challenge asks the question, can we use machine learning on these satellite observations in combination with modern high-resolution terrain data and other ancillary data to fortify the sparse observations currently available via stream gauges? What about those stream gauges, though? While the US stream gauge network is one of the densest and most comprehensive of its kind in the world, it still only represents point sampled at discrete locations. Although this network covers major streams across the US, supporting science, disaster response planning, and most importantly, policy guidance, these observations only offer small fractions and cover only a small fraction of the US stream network. Indeed, the vast majority of the remaining streams in red, or 97% of streams in themselves, missing many small streams not in the map at all, have no observed data on frequency of flow or current state, and of functional characterizations that have not been updated in over half a century. Moreover, the amount of streams missing from the current dataset represent a huge unknown volume of water whose eventual assessment is required for reliable drought and flood prediction in the future. In the next section, we will outline the data and methods that we have used over 4 study areas to explore new methods that can be brought to bear on the VOTUS challenge.
So now we have access to always improving satellite imagery, but it still has limitations. I'm going to talk to you about the different satellite data providers. So Landsat and Sentinel are the standard images used for wide area mapping. They offer a total of 8 images per month and 10 to 30 meter resolution. However, these low resolutions make them insufficient for mapping more streams. Another dataset available comes from Maxar. These images offer extremely high resolution images that could be sufficient to map most rivers. But these images are limited and on demand, so we can use them for continuous mapping. So until now, we had these 2 datasets available. And in 2014, the company Planet started populating the large constellation of high resolution, rapid coverage satellites. This constellation provides 30 images per month at 3 meter resolution. So to sum it up, there is Planet providing 1 image per day at intermediate resolution, and Maxar providing 1 image but at very high resolution. So our approach is to take advantage of the different sensors having different resolutions, so Planet with the 1 image per day and Maxar with a very high resolution, and also to leverage the elevation map provided by the USGS that has the information about where the valleys are and therefore where we might observe water. And what we have observed is that excluding one of these data sets greatly reduces our ability to identify streams. So we use all this data to train a machine learning model to obtain water detection map on each image as an output and study how well we can map the water presence on the surface as a function of time based on this novel high-resolution imagery. So more specifically, let me tell you how our algorithm works. So we have a multi-day planet time series, and this fused in a single representation using 3D convolutions. Now, the other input is the elevation data at a different resolution. We downsample it to the same size as the planet representation and fuse it. We'd like to obtain as an output of the model an image representing the water detection per pixel. This is called a semantic segmentation problem. For this, we input this user representation to a modified unit, a state-of-the-art architecture for semantic segmentation problems. Now, to train our model, we need to give it some examples of what is wet and what is dry. But this is complicated with the planet images. It would be even complicated for a human. So this is where the Maxar images that we're talking about at higher resolutions come in. For our challenge, the USGS, one of our partners, and us use Maxar images to create an extensive data set of labeled polygons covering many small areas, many small and larger streams. Those are at 0.5 meter resolution, which allows to draw more precise labels. And we apply those then to the planet images to train our model on. And this is what allows us to obtain a high resolution output that until now wasn't available at daily predictions. And we call this model the 3D multi-headed unit.
So what has VOTUS achieved? In the background, you see a sample of our water detection map based on high-resolution Maxar in one of our areas of interest, South Dakota. You easily recognize the granularity and detail we achieved. On the side panel, you see a roughly 8 kilometer wide sample of how we improved over the state-of-the-art established by Peckel et al. Attesting to the veracity of our products, we reproduced all detections made by Peckel et al, but also offer many more small streams and also standing bodies of water that come out in great detail in our data. Daily planet imagery also allows wet pixel identification over time. While shadows cast from the walls of many small canyons still cause some false positives in the scene, variability is greatest along the smaller tributaries of the scene, as well as along the banks of the large river, which is exactly what we would expect. Such time series allow for categorizing each stream to update and expand the national hydrography dataset, as well as to assess surface runoff over time in correlation to precipitation and an array of other parameters to establish more precise forecast models. From this, an online interface akin to Google Maps can be developed that could visualize real-time daily data, including the respective red pixel identification and derived predictions. Now, to wrap up, the waters of the United States, particularly streams, are a matter of space and time. The already mentioned National Hydrographic Dataset in conjunction with the National Stream Gauge Network aim to map and monitor the rivers of the US and therefore assess water availability. However, both suffer from inherent problems, with the dataset being outdated, incomplete, and difficult to update. The Stream Gauge Network, with its finite number of stations, is costly to maintain and expand, and thus only captures a fraction of stream activity in the US. The VOTUS approach offers a solution to these problems by utilizing remote sensing data of high temporal and spatial resolution. Machine learning allows for automated mapping to refine a hydrographic dataset, and daily coverage enables verification updating of stream categorizations therein, as well as to assess stream activity over extended periods of time in areas that are optically cooperative. This will enable regional predictions of water availability, the importance of which become clear once we consider that in the US, droughts and floods have caused an estimated $236 and $126 billion worth of damages, respectively, since 1980, second only to hurricanes. Thank you.
Thank you so much to our Waters of the United States team. So I'm going to invite the whole team to join us back, as well as our panelists, for our last question. So for this question, I'd really like to know what stood out for you in that presentation. And to kick us off, I'd love to go to Aaron.
Yeah. So beyond the number of stream gauges in the East versus the West, again, policy implications because of how contentious water policy related to water quantity, not to mention water, there was how much water quantity, not to mention water quality, how contentious that is in the US right now. So yeah, this is great importance and applicability.
Great, thank you, Aaron. And now we're on to Rodney.
So the one thing that really stood out to me as part of this presentation was clearly the more qualitative visualization, where you could see the dramatic improvement in identification of the stream from the state of the art to what this team was able to come to as part of their work this summer. One sort of half-baked idea that struck me when I was thinking about ultimately what the goal of this team was, is the identification of these streams was the first team's presentation on Moon for Good, and their attempt to actually map out sources of water. And now, maybe many generations from now, when we have a sustained lunar presence, this same sort of capability could be transferred to support a similar sort of philosophical and conceptual approach about attempting to recruit these same capabilities, not just for water in the United States and on Earth, but water on the Moon.
Thanks, Rodney. That's really interesting. I think that would be a really unique capability with this team could help out with. And Scott, closing us out.
So in wrapping it up, I think, Sarah, what we've seen a theme here today, which is you've got this fusion of regular science with AI at a scale of cloud doing amazing things. And here in general, the theme here today also is that water is perhaps the most scarce and valuable resource for human existence. And now we have two teams that are now showing what happens when you marry those two technologies together and just doing astounding early work. And I encourage them to continue. And I think, as Rodney said, I want to see these on the Moon and within weather forecasts and all over this just needs to be part of life.
Great. Thank you, Scott. And thank you to our panelists and to Team WOTUS. Amazing work. So we're going to take a short minute while you guys take up the voting. So make sure to vote for your teams, and we will be with you in just a moment. All right, welcome back. Thank you so much for sticking with us. And now is the exciting part where the audience gets to vote, and we're going to share the awards with this team. But first, I'd like to ask James to say a few words.
Thanks, Sarah. I just really, I'm still kind of recovering from the presentations, and I'd say actually we've just had the exciting part, because really the work that was shown today is really blown us away, and I wanted to just thank every single researcher and of course the faculty for helping us achieve what was achieved. It's really mind-blowing actually, and we're thrilled and really proud of what you've done. The image that is showing at the moment is our sort of vision. We're calling it the Astro Repo. As Sarah said at the beginning of today, we really want to make this work available for everybody. FDL exists for all humankind. And of course, if we can't share the work and the results and the data, it means that other people can't follow in the footsteps of our researchers. So our vision is to build this tool, which we're calling the Astro Repo. And this is a little bit like if you like, a launch pad for researchers to continue the work. It'll be full of all the enhanced data products that our teams produce. And of course, also access to the notebooks with the workflows for Starry Spider and Wotus and Crisp and Horus and Pikajoule and those other things that you saw today. So this is just a sneak preview of what we have up our sleeve. And we're really looking forward to making this live in the next few months.
Great, thank you, James. And now I'm going to invite Bill up to help me with these awards. So Bill, can you please tell us what the Collaborative Spirit Award is?
Sure. Well, I think, Sarah, that we saw the collaborative spirit in play today across the board with all the teams. Again, as we mentioned at the very beginning of this, the collaboration that had to take place this year was a virtual collaboration, not just between the team participants themselves, but with their mentors, subject matter experts, industry partners, and so on. So I think it's been extraordinary to see the results that these teams achieved today. And I think they kind of validated with a big affirmative the three questions that NASA sought to answer 5 years ago in terms of AI, ML, and its efficacy for space science and this kind of research. So really a big congratulations, wonderful job to all the teams, great presentations, and so exciting to hear the results. The Collaborative Spirit Award, this one is actually chosen by the FDL faculty. So that's kind of the team here has chosen this year's winner. The Collaborative Spirit Award is the representation of FDL's beating heart, basically interdisciplinary research. That means bringing people with different backgrounds and different disciplines together to work collaboratively. It supports the idea that to achieve great things, 2 or 20 minds are better than one, and the exchange of knowledge is key.
All right, and the winner of this year's award was actually a tie. So we had the Astronaut Health Team, Team Wotus, and Francesco. So well done, teams. Thank you. And now we have Heroic Comeback. What is that one, Bill?
All right, so the heroic comeback is an acknowledgement that when discovering something genuinely new, you have to first fail. But that's only half of the story. Simply failing isn't enough. Getting back up, dusting off, learning, evolving, and trying again is how legends are made. And we saw lots of that today. So this was another faculty chosen award. Have we frozen?
Have we lost Sarah?
We might have lost Sarah. And that means we are like on standby, not knowing who won this award.
Well, it's appropriate because this is Apollo 13 on this award.
So, James, I don't suppose you happen to know who the winner is?
I don't. I have no idea.
Uh-oh. Well, we need to have Sarah come back.
Bill, perhaps while we're waiting, which of the presentations today did you really get inspired by, apart from obviously all of them? But we didn't hear from you. I'd love to hear what you thought.
I thought they were brilliant. I thought they were all inspiring, to your point, and it's really hard to pick one out. I think that most importantly, these are complex problems, and AI tools and machine learning tools aren't necessarily intuitive by any means. And it's hard to grasp what they are exactly, how they work, how they get applied, and what kind of results we got. So I think, for me, one of the big takeaways going across the board, and not letting you pin me down on which one I like the best, I'll cop out on that, but was simply the fact that I think all the teams did a really terrific job condensing, complex stories and 8 weeks of incredibly intense effort into these short and visually impactful and meaningful presentations. I thought that was, for me, the biggest takeaway. And certainly, we hear things like startup coming out of the team that was doing astronaut health because of the potential impact there. But I think so many of the different teams' research projects have applications and implications that go beyond the work that they were doing and beyond the particular domain that their work was being applied to. So I think that's what's also really exciting here, is to watch how these tools and techniques that the teams developed are going to evolve and perhaps be applied to other problems and challenges, and also to be continued to apply to the work that they were doing, because I know the teams have to do their tech memos, and there'll be teams presenting at conferences around the world, and potentially doing write-ups in peer-reviewed journals, which we've seen from FDL in the past. So really, really looking forward to all of that.
Great. Thank you so much, Bill and James, for helping me out there during that break. So I think
a solar flare or something else that.
Yeah. So I'm going to go ahead and keep on going here with our awards. So hopefully everybody can see this.
Well, so Sarah, we never found out who won the last one, the heroic.
Oh no. Okay.
Yeah. You froze, and
I was talking to myself then. So our heroic comeback this year was Satyarth. So congratulations. Thank you so much. Job well done during this difficult FDL. So great. All right. And then I was going to turn it over to you, Bill, to talk to us about what the Unexpected Discovery Award is.
All right. This is always fun. So just like dirty dishes helped the discovery of penicillin, and melting chocolate bars triggered the creation of the microwave, looking for a hearing aid invented the telephone, the Unexpected Discovery Award represents that ability to stumble upon a breakthrough. And as Plato once said, science is nothing but perception.
All right. And you, the audience, voted. So here we are. We will find that out in 1 minute.
Oh, you just have to
live. We don't know yet, huh?
You have to click on the image.
Oh, I have to click on the image?
Or the hide image button. Yeah.
Oh, perfect. Great.
It is the unexpected discovery.
Yes.
Another one.
Great. So this looks like congratulations, the Star Spots team. Well done for winning the Unexpected Discovery Award.
Well done, Star Spots.
That's great. Congratulations.
All right. And most dramatic pivot, Bill.
All right. So the most dramatic pivot. This is, I actually like this expression in its own, because I think, the whole world has had to pivot this year. The SETI Institute has had to pivot. The FDL program absolutely had to pivot, just in terms of being able to do this kind of work in this virtual environment. So pivoting is an action taken when new opportunities arise unexpectedly. Sometimes this means starting completely from scratch after much commitment is put into one idea. The most dramatic pivot award represents these changes in direction, at times unwanted, but certainly necessary.
All right. And the winner is, now that I will click twice.
Now that you've made that
Perfect.
Unexpected discovery.
Great. So that one was for. Okay. Did Star Spots win again? I guess Star Spots won the most.
Yeah, looks like they did. Yeah.
Wow. All right.
Hey, that's the most important star. What am I going to say? I didn't vote.
Maybe
but I think I
somebody
think
loading the ballots.
FDL really wins the pivot.
Yeah, I agree. I agree.
Thank you, Lika. And on to most useful contribution.
All right. Well, that one should be kind of easy to understand, but what defines a contribution? In machine learning, it's often hard to spot the thankless task of data preparation on behalf of the community or the application of a freshly minted machine learning methodology to a new domain. So in some instances, it's something that widens our perception of what's possible. The most useful contribution can be any kind of all of these things, as long as the beneficiary is all of humankind.
And the big reveal here, most useful contribution. Okay. And this also looks like Star Spots took it in the back.
Unbelievable.
All right. And now I believe we're going to move into a special award. So James, I'm going to turn it over to you.
Yeah, so in previous years we've really celebrated this idea of collaboration, and that's really what these awards are for. It's not really about winners. It's just about celebrating the culture that makes for great world-beating work, which I think we've all seen today. But every so often, when you're doing high risk, high return work, things don't go to plan, and we're really dependent on our faculty and really dependent on the expertise that we're able to bring to bear on our projects. And we wanted to make a new award to celebrate this, and this award is based on the story of Apollo 12. Apollo 12 was hit by a lightning strike pretty early into its launch sequence, and the entire command module was rendered dead. So essentially, they had no controls. They had nothing except a radio link to Econ in mission control in Houston. And John Aaron, who was sitting on the Econ desk, was the only person who actually realized what had happened, but also had the presence of mind in the heat of the moment. Can you imagine this gigantic spacecraft hurtling at multiple times the speed of sound towards space, and everybody saying abort? And he said, listen, can you just move the C switch or the SSE switch to aux? And sure enough, the astronauts did this and saved the mission. And it was such an extraordinary thing that John Aaron, who was sitting on the Econ desk at the time, was called the steely-eyed missile man, and this is where we get that phrase from. So we decided that we recognize this in FDL, because every so often we have projects which they look like they're struggling, or they're hurtling with no control. And we've become reliant on some of our faculty, but there's one person that we really wanted to call out tonight. And so, Sarah, do you want to go to the next slide? So this is the award. It's for the steely-eyed operator, and we'd like to give this award to Yaron Gal. So Yaron's really been with FDL since the very beginning. He literally was in the first meeting that Bill said at the SETI Institute when we came to talk about the vision of FDL. He's been with us from the very beginning, and we just wanted to acknowledge the extraordinary support that he gives everybody, and often the thankless hours, working with every team. And just to say thanks so much, Yaron. We're very grateful for the insight you bring.
Maybe clap.
Yes, we should. Absolutely. Yaron's been, he's been like a human version of the Google Cloud in terms of how transformative he's been on his own to the program. Just extraordinary.
Great, and we'd like to just say another thank you to all of our partners, Google Cloud, USGS, Mayo Clinic, Lockheed Martin, MIT Portugal, Luxembourg Space Agency, Intel, IBM, NVIDIA, and Planet. Thank you for supporting us for this program. And a huge thanks to the SETI Institute. We really could not have done it without our partners over at the SETI Institute, Rebecca, who has been helping us with our communications, Lee, who's been helping us with our Facebook Lives and other communication aspects, Debbie, who has been instrumental in just about everything, Yvonne, who's helped us get contracts over the line, and Armine, who has been able to help us with our both recruiting and HR for our program and worked with our researchers. And of course, Bill, you're on here as well. And thank you to you and the rest of the wider SETI team, because it definitely does take a village.
It totally does. I have to say also, though, Sarah, I want to take my hat off to you, especially. I love you in the headset and the mouth microphone, because you remind me of those calm and steady voices of both mission control, or the fellows up in the towers doing flight control for airports. I mean, you've been the steady hand throughout this summer and keeping things on track, keeping things moving. Done an absolutely outstanding job, as has the entire Trillium team. And this really has been a collaboration. All of us, Sarah, James, myself, Lika, Rodney, working together over the whole year to put this program together, and together with our partners like Scott and Massey and Shashi and so many others. So it's really been a wonderful, amazing year. I'm still just blown away by how the teams performed in this most challenging environment. And I hope they actually get a chance to meet each other in person at some point, and that we get a chance to meet them all in person and celebrate together in person at some point. But what an extraordinary year, an incredible ride, and great work to everybody involved across the board, from partners to staff to NASA colleagues, and of course the participants and mentors. Just wonderful work, and thank you so much.
Great, thank you, Bill. And thank you to our production company that was helping us today, Earth Coast. Amazing work.
Great job.
And I don't think we could say it enough. I don't think FDL would have been possible in this virtual environment without Google Cloud, and for not only their compute support, but also just the amount of hours that they've spent with us, the amount of just like brain power and knowledge that these experts bring to our teams. And of course, Bill mentioned it, but I also have to say that our Trillium team has been just amazing. It's been great to have John and Leo, who have been working tirelessly in the background, and all of the beautiful design work that you see is just their brilliance. You have Jody, who I could not thank enough, and really, if she wasn't here, wouldn't have my head straight. And Belina, who has worked with the teams and been able to help them with collaborations and the presentations that you saw today. Richard, who has helped them with their compute and the resources and being able to help teams manage data. And of course, James and Sarah. James, I can't say enough about how much that you have done for this program as well. So.
I think I want to say, like what my old mentor used to say, thought generates action. And if there is anything that epitomizes that statement, I think FDL in general, but virtual FDL in specific, we decided to do FDL virtual somewhere like late February, early March, and from that to where we came to with 8 topics. It is absolutely incredible. And we can't name all the names we need to name that made this a success. But it is a testament to what we can do when we put our energy into doing something that's positive, that benefits all of humankind. I cannot thank all of you enough.
Absolutely. And thanks, Lika, to NASA as well, because NASA was the inspiration behind this program from the very beginning, with certainly a lot of creative help from James and the team. But NASA's foresight into asking those 3 questions 5 years ago and being behind this program over the 5 years, and NASA Ames and our partnership there with Eugene too, and the team and Rodney, it's been transformative. So it's just wonderful to see NASA continue to be such a leading light of inspiration and amazing work. And hopefully the FDL team, lives up to that NASA reputation.
Thank you, Bill and Lika. And with that, I think that wraps up our program. So I just wanted to say thank you all as the audience for joining us. And we really appreciate you tuning in to our FDL showcase.
Very much so. And congratulations, all of you on the teams. You did just an amazing job. Just amazing. Thank you so much.